Hello and welcome to Season 4 of Rex's Hangar, as requested by many of you who enjoy binge watching or binge listening to hours of me talking about old aircraft, so please enjoy. Episode 1, the Bellanca Aircruiser. Today we're looking at two aircraft that are not very well known outside certain aviation circles. The Bellanca Aircruiser, or the Airbus depending on what specific model you are looking at, and the even more obscure Bellanca Model 77-140 bomber. The development of the latter was directly related to the development of the former, hence why both are being included in this video. Also, I apologise if the technical details are a bit lacking for this particular video, but the sources on these planes are both scarce and sometimes conflicting, so I shall only discuss what I'm confident to be true. The Aircruiser can trace its origins back to 1928. In that year, Giuseppe Bellanca built the Bellanca Model K for Italian World War I ace Cesare Sibeli, who had commissioned the design of an aircraft that could fly non-stop from New York to Rome. Unfortunately for Sibeli, he ran out of money and the flight never took place. Bellanca's design survived, however, and he shifted his design focus towards the commercial market. This resulted in the P-100 Airbus and its descendants, the first of which was built and completed in 1930. It was a unique design, both for its looks and its surprisingly high fuel efficiency. It was instantly recognisable due to its wing configuration. Built as a sesquiplane, the lower wing resembled an inverted gull, with a sharp anhedral on the inner sections, and the outer section was especially strange, as it performed the dual role of being a lifting surface as well as a support strut, tapering down to the point where it connected to the upper wing. This unique appearance earned Bellanca's aircraft the nickname of the Flying W in certain places, particularly in Canada. In 1931, the P-100 demonstrated its efficiency by flying 4,400 miles in a single flight that lasted 35 hours. The test pilot, George Haldeman, had mixed opinions about its flight handling. Though it was not outright unstable, it did suffer from aileron drag, and the rudder felt especially heavy, which for long-distance flying was not ideal. However, other than that, the aircraft did perform well. The P-100 did not secure any sales due to reliability concerns over its water-cooled Curtiss Conqueror engine. However, the P-200 and the P-300, powered by air-cooled radials, got a much better reception. Unfortunately, their development was poorly timed. Firstly, the Great Depression reduced the demand for air travel, because everyone was broke, which in turn reduced sales opportunities, and secondly, in 1934, a new regulation outlawed the use of single-engine transport aircraft by US airlines. Though their chance of commercial success in the United States was now all but gone, the Bellancas did see a brief stint of military use. In 1932, the US Army Air Corps purchased 4 Airbuses, and this was followed by the purchase of another 10 in 1933. These would be redesignated as the C-27, and all but one of them would eventually be upgraded as the C-27C, which was powered by a 750 horsepower Wright Cyclone. Capable of carrying a 3,000-pound payload, which was impressive for their size and weight, the C-27s would be used during the 1934 airmail crisis, much like the Douglas XB-7, which we covered in a previous video. The Aircruiser was an improved development of the Airbus. This was conceived before the aforementioned events that curtailed Bellanca's prospects in the United States. It was built as a more luxurious model of the Airbus, but it still maintained the same seating capacity of 12 to 14 passengers. The seats were covered in leather, there was good ventilation for both fresh air and heating, and large cabin windows offered excellent views for the passengers. Ironically, the Aircruiser, designed for luxury and comfort, would find its greatest success as a Canadian bush aircraft. With a more powerful engine than the Airbus, the Aircruiser boasted the ability to lift a payload greater than its own weight at a speed of up to 155 miles an hour. It could also take off in a shorter distance compared to other transports of similar size or weight carrying capacity. These two factors made the Aircruiser suitable for a specific niche in Canada, where a mining boom had created the need for a transport that could carry heavy loads across large distances, whilst also being able to take off from small, remote airfields. The most famous of the Canadian Bellancas was an example purchased by W. Lee Brintnell, who bought it to carry uranium concentrate from the El Dorado mine at Port Radium to Edmonton, and it was dubbed the El Dorado Radium Express. These flights involved supplying the mines on the inbound trip, and then flying out with up to 3,500 pounds of uranium concentrate, worth $20,000 back then, in woven cloth bags. Stan McMillan, who also flew the Aircruiser on this particular route, once said that the Aircruiser was one of the ugliest, most efficient aircraft for its period, and it would continue to fly this particular route for well over a decade. The failure of the Airbus to secure commercial success in the United States, combined with the praise of the C-27 and the Aircruisers, prompted Giuseppe Bellanca to develop a bomber version of the aircraft to offer to the US military, and this resulted in the Model 77-140. This new design featured several major changes compared to its predecessor. The most obvious change was the removal of the nose-mounted engine, which was replaced by a pair of 715 Wright Cyclones that were mounted on the upper wing. They were housed in nacelles that were fitted at the point where the support struts connected with the main wing spars. To both support the additional weight of the engines and also maintain the required lift, the upper wing was both strengthened and had its span increased from 65 feet to 77 feet. Like on the Aircruiser, the upper wing was constructed of two spars, but the ribs were more closely spaced together to improve load handling. The wing itself was entirely fabric covered, and despite looking like a fixed unit, the outer section, along with its lower counterpart, could be folded back for easier storage and transportation. The center section of the lower wing, which supported the landing gear, was built from a steel frame and clad in duraluminum paneling. The design and arrangement of the control surfaces, particularly on the tail, were modified so that control of the aircraft could be easily maintained under the power of just one engine. The addition of two auxiliary rudders on the tail unit is the biggest of these particular changes, and they allowed for single-engine flight without maneuvering the aircraft into awkward positions to maintain control. In terms of crew members, the few scraps of source information seem to wildly vary between as little as 2 to as many as 6. However, the stations on the aircraft, as well as the defensive armament, give some indication on what it should have been. There was, at the very least, a gunner in the nose, of which several photos make this glaringly obvious. On the prototype, this front turret was enclosed, but it was later changed to an open turret for all other models. Then you had the pilot, which was apparently necessary unless you wanted your plane to be a static display, so that makes 2. Then there was a bomb aimer's station, which was located to the right and just below the pilot's seat, so that's 3. And after the pilot's cockpit was the main cabin, which we'll get to shortly, and behind this was the rear gunner's station, so at the very least, you needed 4 crew members. Due to the aircraft's high payload capacity and good range, it was designed to fill a number of roles as needed. Firstly, as a bomber, it could carry over 2,800 pounds of bombs and ammunition. The bomb load itself could consist of a pair of 1,100-pound bombs, or a collection of smaller bombs ranging from 600 down to 100 pounds in various loadouts. Secondly, it could be operated as both a troop transport and an ambulance, courtesy of the large central cabin. It was particularly well suited to the role of an ambulance, and had it been used as such, it would have done well. In terms of capacity, it could easily carry 9 stretchers, plus all the relevant attending medical personnel and equipment. Loading the wounded onto the plane would have been made particularly easy, as there was a large door on the starboard side that was used for cargo loading. Thirdly, its range and good fuel efficiency meant that it could be operated as a reconnaissance plane, and indeed this was particularly emphasized to the US Navy, as the aircraft was also being designed as a float plane. In 1934, its 1,500-mile range, the carrying capacity to carry a 300-pound payload, and a top speed of 175 miles an hour would have made it one of the best-performing aircraft in its class. But in the end, neither the Army Air Corps nor the US Navy were interested. Ultimately, the only customer to purchase Bellanca's bomber would be Columbia. The Colombian Air Force placed an order for 4 bombers to be modified as seaplanes, which were known as the Model 77-320. These aircraft entered service in 1935, operating mostly out of coastal air bases, and they would continue to do so until 1942, though none of them took part in any combat during the Second World War. No example of the bombers can be found today, but 2 examples of the aircruisers are known to exist. One of them is the last flying aircruiser, built in 1938, and it's on display at the Erickson Aircraft Collection in Oregon. The other is the famous plane from the El Dorado Radium Express. It crashed in northern Ontario in 1947, but it is now undergoing a restoration project with the Royal Aviation Museum of Western Canada, and hopefully we'll see it returned to its former glory sooner rather than later. Episode 2. The Bonney Gull. This wacky-looking plane was the brainchild of Leonard Warden Bonney, and although it looked somewhat insane, the Bonney Gull was in many ways very innovative and ahead of its time. Leonard Bonney was an aviator who fell in the category of that first wave of pioneers that sprang up between 1900 and 1914. In fact, he was lucky enough to be taught by Orville Wright, who gave him his flying lessons in 1910, and he flew with the Wright exhibition team that operated during 1910 and 1911. Bonney quickly proved to be a gifted but careful aviator, and in his early years he also had that most important quality of all, luck. Not only did he complete multiple demonstration flights in the Wright Model B pusher without incident, but he also survived a serious crash in a monoplane when, at 1,200 feet, the elevator cable parted and he lost control. After this, most of his early aviation career was spent as a test pilot and instructor at various companies between 1912 and 1914. Uninterrupted employment in those days was hard to come by, as the aviation industry was still in its formative years, and he often moved from job to job. This, combined with being an instructor for both the Army and the Navy during the First World War, gave him a broad wealth of experience with different aircraft. And so, by the mid-1920s, Leonard Bonney was considered an experienced aviator who had a thorough understanding of aircraft design, which made it all the stranger when he decided to design and build the Bonney Gull. In the earliest days of aviation, many flying machines had been built to imitate the wing shapes of various birds, but this had proven to be an impractical approach. However, Leonard Bonney was somehow convinced that he could do better than his forebears, and finally achieved the perfect wing form, thus ushering in a new generation of sleek, bird-like planes. He had decided to base his wing design off that of a seagull, a bird that he was incredibly fond of, and he went through great pains to achieve as close an imitation as possible. This included, but was not limited to, taking plaster casts of a seagull's wings, and tying various weights to some unfortunate seagulls to see how much they could lift. Neither experiment was looked on with kindness by the seagull, and I expect he received many a shrewd peck in retaliation. The task of building the physical attributes of a seagull into his plane was a daunting one. However, Bonney persisted. He was also thorough, building multiple models with alterations and improvements with each iteration, and he also had one tested at a wind tunnel operated by MIT. Work eventually began on the full-scale Bonney Gull in 1926, with construction being done with the help of the Kirkham Company, who had experience in building one-off aircraft, though perhaps nothing as ambitious as this. The design of the aircraft was as unique as it was innovative. For one thing, it was a low-wing cantilever monoplane, and one whose wing was of metal construction and had no exposed struts or wires, which was certainly considered a very modern concept in 1926. It featured an enclosed cockpit, again an uncommon feature for the time, and this held 2 comfortable leather seats and a modern instrument and control panel. The landing gear too was advanced. The main wheels were connected to the fuselage with single streamlined struts, and they had independent brakes. Unlike many aircraft at the time, which featured tail skids, the Bonney Gull had a steerable tailwheel housed in a streamlined fairing. By far and away the most modern aspect of the Gull was the construction of the wings and control surfaces. Leonard Bonney wanted his plane to be able to take off and land in as short a run as possible, and so he poured a huge amount of time and effort into the design of the bird-like and incredibly complex wings. Not only did they feature strong dihedral and anhedral, thus resembling that of a gull, they could also be folded back for easy storage, and they also had two design features that would not make a mainstream appearance for decades to come. Firstly, the Bonney Gull featured variable incidence flight surfaces. The wings had a normal angle of attack of 10 degrees, however it was able to pivot around the main spar to increase this angle all the way up to 45 degrees. This was done by a hydraulic mechanism that was controlled by the pilot. Under normal operation, the wings would be put to the sharpest angle of attack upon the moment of landing, thus acting as a speed brake and significantly reducing the distance required for a safe landing run. Whether Bonney intended to operate the wings in this way during flight as well as landing remains unknown, for reasons that we'll come to shortly. The second radical design feature was that of variable wing sweep. The inboard section of the wings featured large flaps, however the outer sections of the wings were designed to sweep forward and backwards through an arc of 20 degrees, and they were also hinged to act like ailerons. Like the angle of attack, this too was controlled by a mechanism in the cockpit, which, combined with everything else, would have made flying a somewhat complex affair for the pilot, as everything had to be done manually. By the end of 1927, the Gull was all but complete, and it was finished with a 9-cylinder, 180 horsepower Kirkham radial engine. Though it may have boasted advanced design features, the Gull, with its fat body and odd-looking control surfaces, did not look easy to fly, and Leonard Bonney struggled and eventually failed to find a willing test pilot. And so he did it himself. In early 1928, he completed a test hop which ended up breaking the landing gear. However, this was repaired, and by early May, he was ready to perform the first test flights. Despite the pleas from friends, colleagues, and several fellow aviators who had known him for years, he prepared the aircraft for takeoff from Curtiss Field on the 4th of May 1928. Now, there is some video footage of the first and only flight of the Bonney Gull. However, I didn't feel like A, paying £300 for a non-perpetual license of a 60-second clip that would expire after just a few years, or B, receiving a copyright claim for posting an unlicensed video, and so we're just going to have to deal with some still photos instead. Thank you, British Pathé. But, grumbling about the cost of footage aside, Leonard's first flight did not go well. After an initial takeoff run that almost ended in a ground looping incident, the Bonney Gull raced across Curtiss Field and lifted into the air. All seemed to be going well as it made its climb, but at around 100 feet it suddenly pitched over, and the plane nosedived into the ground. Leonard Bonney was thrown violently from the plane on impact, suffering serious injuries, and despite some news articles at the time claiming he died on impact, he was, in fact, taken to hospital where he would sadly succumb to his injuries later that day. There is no definitive answer for what caused the accident. Some suspected a control cable failed, others thought that the plane was simply just unstable, and a few thought that Leonard Bonney had perhaps pulled the wrong lever in his cockpit. Whatever the cause was, the world was thus deprived of a forward-thinking, albeit somewhat eccentric aviator. Episode 3. The Fleet 50. The Fleet 50 freighter was an attempt by Canadian manufacturer Fleet Aircraft to make a general utility and transport plane. In the 1930s, Canada was experiencing a mining boom, and while several aircraft types had been imported for use as bush transports, Fleet wanted to develop a Canadian-built aircraft for this role, and thus give some much-needed expansion to the post-Great Depression aviation industry in Canada. They set out to build a twin-engine biplane that could haul large cargo loads, large being both in weight and in physical size.
Design work began in 1936, and not long into this process, the decision was made to design it as both a land plane and a float plane, owing to A. Canada's large coastline, and B. the enormous quantity of lakes. The fuselage structure was constructed of welded steel tubes and mostly clad in fabric, the exception being the nose, which was constructed as a semi-monocoque and clad in duraluminium. The fuselage had room for 2 crew members and a large quantity of cargo, and to improve logistics on the ground, between 4 to 5 large doors and a roof-mounted chain hoist were installed. The wings had an equal span, but the lower wing was built as an inverted gull, and it's possible that the designers had taken inspiration from the Bellanca Aircruiser, which we covered in a recent video, but there is no solid evidence to back that up, though they do look somewhat similar. The center sections of the wings were of all-metal construction, with a stressed metal skin, and the outer wing sections were constructed of wood and clad in fabric, with the sole exception of the leading edge, which was also covered in a metal skin. The prototype was designated as the Fleet 50J, or the Model 46K depending on what source you're looking at, and this was completed with 2 7-cylinder, 285 horsepower Jacobs L5 MB radial engines. These were mounted on the upper wing and were supported by no less than 6 struts connecting to both the fuselage and the wing itself, and the prototype flew for the first time on February the 22nd, 1938. From the beginning, things did not go well for the Fleet 50. The first flight tests revealed that it was woefully underpowered, not an ideal situation for a transport that would operate in and around the Canadian Rockies, which prompted the upgrade to a 330 horsepower version of the Jacobs engine. Whilst this was going on, 4 more aircraft were being built, and these were completed as the Fleet 50K. Some of these went to private owners at first as bush transports, and at least 2 of the 5 planes built were also modified to be able to carry up to 10 passengers in relative comfort, as even the improved Jacobs engines were found to be still too underpowered for heavy cargo transport, and it was thought that passenger transport might be a good alternative. However, any hopes of marketing the plane as a passenger transport went up in flames. Literally, when the demonstrator sent to the United States caught fire in front of a group of officials and potential buyers and was burned to a crisp. Back over in Canada, a series of incidents and crashes, courtesy of the underpowered engines, had left a bit of a poor first impression of the Fleet 50. However, despite a tendency to want to fall out of the sky, its large fuselage and multiple loading doors were highly praised, and it was considered one of the easiest cargo planes to both load and unload. It was also one of the first aircraft to ever have a nose door, which gave access to a cargo space under the cockpit that ran the whole length of the fuselage. The Royal Canadian Air Force acquired 2 of the aircraft for a brief period of time. These were first used as paratroop training aircraft, but then later on in 1943, one was used as an air ambulance and the other as a float plane trainer. However, the RCAF also found them to be dangerously underpowered, and these were eventually sold. In general, the experiences of those operating the Fleet 50 was short and painful, mostly due to the poor engine performance and high operating costs. As a result of the underpowered engines, the attrition rate of incidents quickly caught up, and one by one the planes were wrecked. One float plane model was sold from the RCAF to the Labrador Mining and Exploration Company in 1944, where it operated for a grand total of 9 days before it crashed onto a beach, after which it was abandoned. This trend was then repeated when the RCAF sold its other plane to Mexico that same year, who only managed 18 months of operations before it too was crashed. The 4th 50K freighter, having been leased by Fleet Aircraft for short times to a number of operators, eventually sold it to Austin Airways in 1945, which then lost the aircraft to fire in 1946. And so, when the last Fleet 50 went out of service in 1946, it was also the only Fleet 50 to go out of service in 1946, or at all for that matter, as the rest were all gone. The remains of one aircraft, the one that was crashed onto a beach and then abandoned, can be found in the Canadian Aviation and Space Museum, but aside from that they are mostly forgotten. Had the Fleet 50 been equipped with a more powerful engine from the start, things may have turned out differently, but it wasn't, and so ends its story.
Episode 4. The Bell X-1.
The development of this historic aircraft began during the Second World War. Fighter aircraft had reached the point where some examples were now capable of reaching high subsonic speeds in a dive. This was an incredibly dangerous situation for the pilots involved, as their aircraft began to act strangely as they approached their critical Mach number. When an aircraft reaches this speed, the speed of the airflow in some areas around it reaches the speed of sound, even though the aircraft itself has an airspeed slower than this. At this point, shockwaves begin to form in the airflow, and when this happens at the control surfaces, it results in a loss of control as the airflow is directed further away from the control surface instead of flowing over it. After numerous accidents had occurred, and indeed after numerous pilots seemingly disappeared during missions after diving down on targets from high altitude, manufacturers imposed limits on aircraft diving speeds, and strengthening modifications were made to several airframes. This only partially remedied the problem, and although further research was being conducted, neither Britain or the United States were putting their full effort into the development of advanced high-speed aircraft. Things changed rather quickly in 1943, when intelligence reports on German jet aircraft reached them, and it was quickly realised how far they were lagging behind. One report by a British agent had details of a German plan for a supersonic jet. Though it was only a design study, it was more than enough to spur the relevant parties into further action, and by the end of the year, both Britain and the US had launched projects to design and build the world's first supersonic aircraft. Britain began development work on the Miles M52, a project that was ultimately curtailed due to politics, but that will be covered in another video in the future. Meanwhile, in the US, work had begun on the assembly of a team to develop their own experimental research aircraft aimed at achieving supersonic speeds. As early as 1935, men such as Theodor von Karman and Ezra Kocher had recommended the construction and testing of a full-scale, specifically built aircraft capable of transonic speeds. In 1944, they would be members of a small team that began investigating the choice of propulsion systems for such an aircraft. The question was, did they go for rockets or jet propulsion? While various experiments with scale models took place, important meetings were held at Langley between the Army Air Technical Service Command, the Navy Bureau of Aeronautics, and NACA. These discussions led to two different approaches to the transonic aircraft project, and this would eventually materialize as the turbojet-propelled Douglas D-5581 Skystreak, what a long name, and the rocket-propelled Bell X-1. During the summer of 1944, Kocher began looking for a manufacturer to design and build the rocket-powered aircraft for the project. This was a laborious task, but after several unfruitful contracts with aircraft manufacturers, he attracted the interest of Bob Woods and the Bell Aircraft Corporation. The first specifications for the Bell design were drawn up in December 1944, and on the 16th of March 1945, the first contract was signed, calling for the construction of 3 aircraft, designated as the XS-1, and within Bell, this was known as the Model 44. At this time, little was known about transonic flight and the associated technologies, materials, airfoil sections, and assembly methods required. All of this was new territory, and pretty much everything had to be invented. For this reason, the decision was made to design the fuselage shape of the XS-1 to mirror that of a .50 caliber bullet, one of the few objects known to be stable at supersonic speeds. It is here that we get onto the delicate topic of research sharing, or rather, lack thereof. In 1944, the British Air Ministry and their US counterparts had signed an agreement to exchange high-speed research and data. By this point, work on the Bell aircraft was well underway, but testing had revealed a problem with pitch control. The problem was then solved when Bell was given access to the research and technical drawings of the Miles M52, which made use of a variable incidence horizontal stabilizer. Tests by both Miles and the RAE showed that this was the solution to dealing with the problem of pitch control, and so this too was adopted on the Bell design. However, when the British wanted to arrange a visit with Bell to get their research data, the Pentagon stepped in and told them no. This understandably gave the British a bitter memory of the collaboration, and that was something that hurt British-American Research Corporation, at least in the aviation sector, for some time afterwards. By October 1945, a full-scale mock-up of the Model 44 was completed and subsequently inspected by NACA and the Army Air Force. In order to save on fuel that would be needed for the rocket engine, the then still under development XLR-11, it was decided that the aircraft would be air-launched from a high altitude. After this mock-up was approved, construction immediately began on what was to become the Bell X-1. The bullet-shaped fuselage was clad in a skin of stressed high-strength aluminium, and it was designed with an especially strong maneuver load factor of 18 Gs. This was made in the interest of pilot safety, as during this time there were no computer simulations for aerodynamic forces, and quite frankly, nobody really knew the levels of force the X-1 would encounter at supersonic speeds. Based on extensive research, NACA requested that the mid-mounted wings have a chord thickness that was as thin as possible. Initially, a thickness of 12% was requested, but this eventually went down to an 8% chord thickness on the wings and a razor-sharp thickness of 6% on the horizontal stabilizer. This was also done in the name of safety, so as to provide the least problems with stability and control as the aircraft entered the zone of transonic speeds. The power plant, as mentioned earlier, was a Reaction Motors XLR-11, and it was the first liquid-fueled rocket developed for use in aircraft in the United States. It gave a maximum thrust of 6,000 pounds at sea level for approximately 5 minutes, and it used liquid oxygen and diluted ethyl alcohol as a fuel. This was stored in 2 tanks. The ethyl was stored in a 300-gallon tank located between the wing trailing edge and the engine, and the liquid oxygen was in a 310-gallon tank that was located immediately behind the cockpit. The cockpit itself was pressurized, and its canopy was shaped to conform to the overall shape of the fuselage. In the original X-1, this canopy was fixed, and the only access to it was through a small hatch on the starboard side. Though Bell had put in effort to make the plane as safe as possible, size and weight constraints, as well as the question of the airspeed simply killing the pilot, prevented the fitting of an ejection seat, and so the only option a pilot had in an emergency was to try and get the aircraft safely down to the ground. The first X-1 was completed and rolled out, minus its engine, at Wheatfield on the 27th of December 1945. It was then mated to the underside of a Boeing B-29 and flown to Pinecastle Field in Florida. Here it began a series of gliding flights to test the subsonic controls and handling, with the first glide taking place on the 27th of January 1946, with test pilot Jack Woolmans at the controls. Following this, 9 further gliding flights were conducted, and with the exception of some unfortunate incidences involving the collapse of the undercarriage, things looked promising. It was then decided to transfer the X-1 to Muroc Air Force Base, but due to requested modifications to the wings, the aircraft was not ready for its next flight until April of 1947. Meanwhile, the second X-1 had been completed, and it arrived at Muroc on the 7th of October 1946. As I'm going to jump back and forth between them a bit here, we'll refer to them as Aircraft Number 1 and Aircraft Number 2. This second aircraft was almost identical to the first. However, its wing chord thickness was 10% compared to 8% on the first X-1, and so it was expected to be the slower of the two, though still incredibly fast. Number 2's first glide took place on the 11th of October 1946, and it was flown by Chalmers Goodlin. This glide was followed by 3 more before the first powered flight of the X-1 took place on the 9th of December 1946. In this first attempt, the X-1 was released from the B-29, climbed to 35,000 feet, and achieved a speed of Mach 0.75, or 510 miles an hour. Several more flights followed this until the arrival of aircraft number 1 at Muroc on the 4th of April. Goodlin also performed the first powered flights of this aircraft, with the first taking place on April the 11th. All of these flights were done at subsonic speeds between Mach 0.72 and Mach 0.77. There was no throttle on the X-1, and the only way of limiting the speed was reducing the number of combustion chambers that were firing, which of course reduced the thrust. Normally, the rocket operated on 4 chambers, but initially it was only running on 1, and then later 2. But even on reduced power, Goodlin was surprised at the thrust behind the rocket when it was fired. Several weeks later, the test flight program was shared between the Air Force and NACA. The Air Force was to explore the transonic and supersonic speed envelope with the first X-1, while NACA would explore transonic stability and control with the second. For the Air Force side of the program, 3 test pilots were selected: Lieutenant Robert Hoover, Captain Jack Ridley, and Captain Charles E. Yeager, who we all know better of course as Chuck Yeager. On the 6th of August 1947, Yeager completed his first gliding flight, followed on the 29th by a powered flight that achieved a speed of Mach 0.85. Following this, the speed was incrementally increased over several powered flights, with Mach 0.997 being reached on the 10th of October. At this point, Yeager had named his X-1 Glamorous Glennis, after his wife, something he had also done with his P-51 Mustang during World War II. And on the 14th of October 1947, Glorious Glennis was carried into the sky for her historic flight. The mission profile was relatively straightforward. The B-29 would climb at 165 miles an hour to the X-1's launch altitude of 25,000 feet. Once it reached this altitude, Yeager would get into the X-1. For safety reasons, he stayed aboard the B-29 during the ascent, and here the B-29 would enter into a shallow dive to pick up speed in preparation for release. Once released and clear of the B-29, Chuck Yeager fired all 4 chambers of the rocket engine and pulled the X-1 up into a rapid climb, quickly racing away from the B-29 and the chase aircraft. The X-1 climbed up to over 40,000 feet, where it finally reached supersonic speeds, achieving Mach 1.06 and breaking the elusive sound barrier. This technological feat was not immediately publicized, and in fact it was meant to be kept secret for a considerable time, had the details of the flight not been leaked to journalists, who subsequently published the news in December. Angered by this, the Air Force threatened legal action, but the cat was already out of the bag, and senior officials simply cursed them privately in backroom meetings whilst getting on with further testing. Aircraft number 2 made its first NACA flight with Herbert Hoover on the same day as Chuck Yeager's historic flight. Both aircraft completed several more flights over the following months, and Hoover would then go on to achieve his first supersonic flight on the 10th of March 1948. During 1949, the first X-1 was used to set several records for altitude as part of a new series of exploratory flights. This was done with Major Frank Everest. On the 25th of July, he reached an altitude of 66,846 feet, and then on the 8th of August, he reached 71,902 feet. Following this, the aircraft was used for several more flights, with the final flight of the first X-1 being completed by Chuck Yeager on the 5th of December 1950. The second aircraft was flown by NACA for a bit longer before also being retired, and the third X-1, which had been hopelessly delayed in its construction, was completely destroyed in an accident where it blew up while still attached to the B-29 mothership. Luckily, nobody was seriously hurt, and although it too was written off, the B-29 at least managed to land safely. This is not the end of the X-1 story, however. On the 14th of November 1947, the Air Force authorized Bell to develop an upgraded version of the X-1 under a new set of contracts. The Model 58, as it was known within Bell, retained the wings, horizontal tail surfaces, and power plant of the original X-1, but it had an entirely new fuselage. The fuselage was 4.5 feet longer. This was done to increase the fuel capacity, and it also featured a new canopy as well as an ejection seat. Of the 4 aircraft ordered, only 3 would eventually be built: the X-1A, the X-1B, and the X-1D. These aircraft were similar in design and only differed in fine details. Featuring a new low-pressure fuel system and slightly increased fuel capacity, the X-1D was rolled out first, and it completed its first gliding flight in July 1951, being carried aloft by an EB-50A. Unfortunately, the X-1D would not have a long life. Things started badly on its first gliding flight when the undercarriage collapsed during landing, and things got decidedly worse when the aircraft decided to spontaneously explode while still attached to the mothership on its second flight. Thankfully, the explosion did not critically damage the EB-50, and it released the burning wreck of the X-1D to fall to the Earth. The X-1A started off with better luck, and it completed its first powered flight on the 14th of February 1953. Like the original X-1, this too was a record setter, and on the 12th of December 1953, Chuck Yeager achieved Mach 2.44 at an altitude of 74,700 feet. The X-1A promptly thanked him for his exploits by then trying to kill him, and Yeager became the first person to experience the terrifying phenomena of roll coupling, or inertial coupling as it's sometimes called, at supersonic speeds. This happens when an aircraft attempts to roll at high speeds, and the centrifugal forces cause it to move about all 3 axes. Long, thin aircraft designs with stubby wings are particularly susceptible to this, and with some future designs, this would sometimes have tragic consequences. After setting more records, which included an impressive maximum altitude of 90,440 feet in 1954, the X-1A was handed over to NACA for further testing. Here it did not last long, for in a mirror of the X-1D, it too decided to explode while still attached to its mothership. Subsequent investigations following this, and the fatal loss of the X-2, of which we will cover in another video, would reveal the culprit of these explosions as the leather gaskets on the liquid oxygen tanks, and these would be quickly removed from the remaining aircraft. The X-1B arrived at Edwards Air Force Base on the 20th of June 1954. The first glide was completed on the 25th of September, and then powered flights commenced in October. After several familiarization flights, it was then handed over to NACA in December. 17 flights were completed with NACA, but further flights and modifications were cancelled when cracks were found in the liquid oxygen tanks, and the X-1B was never flown again. In one last hurrah, the second X-1 prototype would find a second lease in life. In April 1952, NACA began considering the possibility of modifying it with a new low-pressure turbopump unit, as well as modifying the wings to have a chord thickness of just 4%. Eventually, these modifications were carried out, and the aircraft, now known as the X-1E, was ready by late November 1955. In addition to the aforementioned modifications, the X-1E featured a new cockpit and canopy, complete with ejection seat, and was powered by a new version of the rocket engine, though still rated at 6,000 pounds of thrust. Along with the initial gliding flight that took place in December 1955, at least 25 other flights followed, with the X-1E achieving a maximum speed of Mach 2.24 on the 8th of October 1958. At this stage of the program, several minor modifications were incorporated, including the installation of 2 ventral fins in order to improve directional stability. A few additional flights were then logged, but then the program was terminated when cracks were discovered in the fuel tank, and the X-1s never flew again. Though their time was short, the X-1s changed the future of aviation in many ways, and not just because of their immense speeds. They represented the first of a new generation of research aircraft, ones that were built solely for the purpose of experimentation and development, and these would become known as the X-planes. And that is quite a legacy to have.
Episode 5, The Kalinin K-12.
During the interwar years, many countries invested in the development of tailless and flying wing aircraft designs, and the Soviet Union was no exception to this. Several radical designs were built and tested during the 1920s and the 1930s, and today we are looking at the Kalinin K-12. Konstantin Kalinin was no stranger to unconventional aircraft designs. At the beginning of the 1930s, he had designed and built the colossal K-7, which we covered in an earlier video, and it should come as no surprise that he too was toying with the idea of a flying wing or tailless aircraft design. In 1933, he drew up plans for a new bomber aircraft, and submitted 3 different proposals to the VVS Scientific Test Institute. 2 of these designs looked suspiciously normal. One was a conventional monoplane, and the other was a twin-boom design with twin engines, but the third was a more adventurous tailless design. Appreciating that multi-purpose aircraft had a higher chance of receiving approval during a time of tight budgets, Kalinin also included plans for the aircraft to be converted to a transport for civilian use. After some deliberation, the tailless design was chosen as it boasted a lower overall weight, as well as reduced drag characteristics compared to the other 2 models, and Kalinin received approval to develop a prototype that would be designated as the K-12. Initially, development work began with the construction of scale models that were to be used in wind tunnel tests. Though tailless designs had been tried before in the Soviet Union, less than a handful had actually been built, and Kalinin had to make doubly sure that his design would fly, and fly well. The last thing he wanted was to attract the ire of his superiors, and with Stalin being especially trigger-happy with his recent purges, the risks for Kalinin were pretty high. During the early stages of development work, Kalinin had to try his best to both resist official pressure to develop the plane as fast as possible, whilst also at the same time keeping ahead of the competition, as rival designer Cherenovsky was also working on a tailless design of his own. Once the wind tunnel tests had concluded that Kalinin's design should fly, and fly safely, work then began on a half-scale manned glider. This had a wingspan of 9 meters and a length of 5.2 meters. It was constructed mainly from wood and fabric, and it was equipped with a fixed undercarriage comprising of 2 main wheels and a tail skid. The wings had a relatively high chord thickness ratio and were completed in 2 sections. The inner section was flat, and the main spars connected with the mounting points for the fixed landing gear, and the lower section of the outer wing tapered down in thickness towards the wingtip, upon which was mounted the horizontal stabilizer and rudder. Running along almost the entire trailing edge of the wing were a series of slats for added stability, and the ailerons, of which the inner pair could apparently act as flaps. But treat that with a pinch of salt, as I could only find one particular source that claimed that. The K-12 glider was completed by early 1934, and during the following 12 to 18 months, over 100 successful test flights were completed, with test pilot Borisov at the controls. Almost no information survives about the glider or its test flights, but it can be safely assumed that they must have mostly gone well, as construction on a full-scale prototype began in early 1935. Unlike the glider, this aircraft was completed with a frame that was built from chrome-and-seal steel. Some drawings seem to hint at an all-metal design as well, but for reasons we will shortly cover, this never eventuated. There was provision for a 3-person crew, a pilot in an enclosed cockpit that sat above the wing leading edge, a bomb aimer in the nose who could also operate a forward-facing machine gun, and a rear gunner. The intended defensive armament was 2 single 7.62mm Shikast machine guns, however these were never installed on the prototype. It had been intended to power the K-12, which was also known as the BC-12, with a pair of 9-cylinder M25 radial engines, which was a license-built version of the Wright 1820 F3 Cyclone. But these were not available when the K-12 was nearing completion, and so it was fitted with a pair of M22s instead, which themselves were a license-built version of the Bristol Jupiter. Though they developed 435 horsepower, they were deemed underpowered for the task of getting the K-12 into the air. But with no alternative available, the design team had to significantly lighten the prototype before its first flight. This meant that the planned machine guns were never fitted, and the undercarriage, which had been planned to be retractable, was installed as a fixed unit instead. Along with some other changes that involved removing unnecessary equipment from the cockpit and bomb aimer station, the aircraft's takeoff weight was lowered to the point where it was hoped that the engines would bear it, and the first flight took place in July of 1936. Thankfully, the engines did bear it, and after a few more flights to confirm that it was reasonably safe, the aircraft was flown to Moscow in October to undertake trials with the VVS. During these trials, the test pilots gave it a mixed review, with the main complaints being that the central fuselage was too large, and its poor aerodynamics negated the benefits of the tailless design. They concluded by asserting that even with the installation of more powerful engines and a retractable landing gear, the K-12 would not be able to outperform conventional aircraft. This, along with the outbreak of the Spanish Civil War and the general heating up of tensions throughout Europe, prompted the VVS to cancel development of the K-12 in favour of more conventional designs, such as the DB-3. This was also helped along by several political opponents of Kalinin, who had the ears of several well-placed members within the Soviet Air Force. Kalinin's prospects briefly revived in 1937, when the K-12 was allowed to fly in the Ticino Air Day demonstration. For this, it had been repainted in a strikingly bright colour scheme, representing that of a Firebird, and supposedly this impressed several senior officials who then demanded a resumption of testing and pre-production work. What follows on from this differs depending on what source you're reading, and honestly, the clarity on these events feels about as thick as mud. That being said, I shall attempt to provide a balanced explanation. One version of the story goes as follows. When the program was originally cancelled, the factory in which the K-12 had been built, factory number 18, had its resources reassigned to the production of the DB-3 long-range bomber. However, Kalinin took advantage of his position as chief designer, and he diverted some of the factory's resources back to the development of a small production series of 10 K-12 bombers. Because of this, the production of the DB-3 at the factory was affected, and Kalinin was investigated for manipulation of state resources. He was subsequently arrested by order of Stalin, sentenced, and shot on the same day, October the 22nd, 1938. The other version of the story states that the production of the 10 K-12s had indeed been authorized by senior officials, who had been impressed by the aircraft's demonstration. This had angered Kalinin's rivals, who had hoped that the project's cancellation would put him out of business, and they had conspired to get him arrested on trumped-up charges of spying, for which he was arrested by order of Stalin, sentenced, and shot on the same day. However, this source puts the date of his execution in 1940, which seems to conflict with most other sources, which by dint of accuracy makes the previous story the more likely scenario. The true story of Kalinin's death may never be fully known, but it is clear that the 10 incomplete models of the K-12 were scrapped, and the Kalinin Design Bureau was disbanded. Before his death, Kalinin had hoped that his tailless aircraft would lead on to more advanced designs, such as his envisioned K-14 medium bomber and the even larger 4-engine K-17. But this would never come to pass. And so ends the story of the Kalinin K-12.
Episode 6. The Curtiss SOC Seagull.
In the early 1930s, the US Navy was looking for a new catapult-launched observation plane to replace the Vought O2U and O3U float planes, and in answer to a new specification, they received submissions from Vought, Douglas, and Curtiss in early 1933. The design submitted by Curtiss appeared to be a throwback to the 1920s, at least on first appearance. Their prototype model, the Model 71, which would later be known as the XO3C1, was an equal-span biplane design with moderate wing stagger. The fuselage was constructed of welded steel tube framing, and although it was covered with aluminium paneling on the front, the rear was clad in fabric. The wings too were covered in fabric, and they were built on an aluminium frame with fabric-covered control surfaces. As with most aircraft of this type, these wings could be folded back against the fuselage for shipboard storage. The prototype had a pair of open cockpits for the pilot and the observer, something that was rapidly falling out of fashion by this time, and it featured an amphibious landing gear that retracted into the large single float. As it was to serve at sea, and possibly also crash at sea, the crew had a fair amount of kit on board. A life raft was stowed under the pilot's seat, a first aid kit was stowed under the rear gun, a toolkit was on the forward side of the firewall, and a watertight map case was on the lower port side of the front cockpit, and both crew members of course had a flare gun. The features that could be considered modern on the plane were relatively few. It had full-span leading-edge slats on the upper wing, trailing-edge flaps on the upper wing as well, and a streamlined cowling around the engine, which was a 9-cylinder Pratt & Whitney Wasp that produced approximately 500 horsepower. And as far as modern things go, that was about it. Although aspects of the Curtiss prototype could be considered basic, or even outdated, this did not represent any sort of regression in their design thinking. In a time of American isolationism and reduced budgets, courtesy of the Great Depression, Curtiss designers knew they needed a plane that was cheap to build, relatively modern, and sturdy enough for a life at sea. And so they made their design modern where it needed to be, with the new control surfaces improving the aircraft's low-speed handling, and cheap where it could afford to be, having most of it covered in fabric and made from basic materials. This design approach paid off, as after competing in trials against the Douglas and Vought prototypes, the Curtiss prototype was deemed the overall winner, and the company was awarded a contract for 135 production aircraft. The aircraft was first built as the Curtiss X03C1, but then this was updated to the SOC1 after approximately 6 months. This change in designation followed the merging of the scouting and observation roles for ship-launched aircraft. Previously, observation types were deployed on battleships, and scouting types were deployed on cruisers. Now they performed both roles. Compared to the prototype, there were some improvements made to the production model. Firstly, a large canopy was added that enclosed both cockpits, and this was streamlined into the tail by a collapsible turtle deck that could be lowered to allow the rear gunner a clear field of fire. The production model also featured a more powerful version of the Wasp engine, now producing 550 horsepower, and the engine now had a full NACA-style cowling. Changes were also made to the undercarriage. The amphibious unit was removed, and production models would either come with a standard float for use aboard ships, or a fixed undercarriage for use aboard carriers or when deployed to coastal airfields. Deliveries of the first SOC-1s began on November 12, 1935, with the light cruiser USS Marblehead being the first ship to officially receive its aircraft. In terms of operational use, with the exception of carriers, all SOCs operated on a single float and were launched from shipboard catapults while at sea. After completing a mission, the recovery process was rudimentary but effective. The ship would make a large, sweeping turn by which the ship's wake would produce a relatively calm area of sea for the plane to land upon. Once on the water, the pilot would taxi alongside the ship, which would be towing along a so-called plane trap, which was basically a giant reinforced net. The plane had a rearward angled bar that acted like a hook underneath the float, so that when it came up over this net, the pilot simply had to power down for the plane to be caught. The observer would then attach a hook that was lowered down by the ship, and the plane could be hauled up. Multiple versions of the SOC-1 would be built during the 1930s. After the completion of the initial production order for 135 SOC-1s, an order for 40 land-based SOC-2s was placed. Aside from the fixed landing gear, this model also had another improved version of the Wasp engine, this one being the R1240-22. And not long after this, an order of 83 SOC-3s was placed. These were identical to the SOC-2, but their landing gear was designed to be easily interchangeable with a float. Additionally, some versions of these two models were later used for carrier operations, and they would be known as the SOC-2A and 3A respectively. The last 3 SOC-3s from the production order were modified and given to the US Coast Guard as the SOC-4, However, these were later reacquired by the Navy in 1942 and modified to SOC 3As. To comply with a naval policy to build 10% of its own service aircraft, 64 SOCs were ordered from the Naval Air Factory. These were generally equivalent to the SOC-3, but they were designated as the SON-1 and then later the SON-1A for the aircraft modified to again operate on carriers. The SOC was not known as the Seagull until 1941, when it became commonplace for the Navy to adopt popular names as an addition to the aircraft's official designation. However, by mid-1941, all battleship observation squadrons had now been equipped with the newer Vought OS-2U, and most Seagulls were in reserve units. Following the attack on Pearl Harbor, things quickly changed. The SOCs were quickly pressed back into frontline service, with almost all cruisers in the US Navy operating the plane in 1942. A new type of operation for the aircraft began in 1941, when several SOC-3s were converted to the SO-3A for carrier use. The first 12 of these served with Brewster Buffaloes aboard the first escort carrier, USS Long Island. By late 1942, 4 other escort carriers were operating the Seagull in the Pacific, and they were also operated by the USS Charger in the Atlantic. Their return to service life was partly due to the war, but also due to the fact that the Seagull had managed to remain superior to the aircraft designed to replace it. By the spring of 1938, the production of the Seagull had ended, as work had already begun on a monoplane scout aircraft to replace it. However, this new plane, the Curtiss SO-3C, proved to be a colossal disappointment, and its hasty withdrawal from service kept the old Seagulls relevant until 1945. Ultimately, 322 Seagulls would be produced, and they would cease service in the Atlantic and Pacific Oceans, as well as the Mediterranean. Generally, they were very well liked by both their pilots and the crews that serviced them. Unfortunately, no example of this naval workhorse can be found today, which is a shame as it's an often underappreciated plane.
Episode 7, The Christmas Bullet.
Today, we're taking a look at a plane whose story would better suit a satirical comedy rather than an actual page of history. But fate is a cruel and often sarcastic mistress, and what follows is indeed a true story. A story of lies, money, more lies, and badly built planes with wings that fall off at random. I am, of course, talking about the infamous Christmas Bullet. It got its name from the interesting man who designed it, Dr. William Whitney Christmas. Born in 1865 in North Carolina, he was either one of the greatest con men of his generation, or he was one thoroughly misplaced daydreamer. Despite having no background in aeronautical engineering, or engineering in general for that matter, he arrived on the scene in the late 1900s, claiming to have designed, built, and flown his own aircraft in 1908, which would have made him one of America's pioneering aviators. There was just one problem: this supposed plane didn't apparently exist. Some sources seem to conflict on the reason for said plane's absence. One story goes that Christmas claimed he burned the aircraft and its design drawings to prevent his ideas from being stolen. Another source claims that the aircraft was destroyed in a flying accident. Either way, it no longer existed, which meant people could only take Christmas at his word that he was indeed a qualified aviator. Apparently, the good doctor was rather convincing with his tales, as he was able to found the Christmas Airplane Company in 1909 with the help of some investors. Supposedly, that same year, he designed and built a biplane that he nicknamed the Red Bird. This was apparently flown in 1909, but there seems to be questionable, if any, actual evidence to support this. According to him, though, it was a success, and he was able to give up his career in medicine to pursue aviation full-time. Over the next few years, the company changed hands and investors multiple times, and along the way it dodged the occasional lawsuit for deception or even patent infringement. Things could have gotten quite messy, but the outbreak of the First World War provided Christmas with new opportunities to develop and sell his supposedly revolutionary designs. In 1915, he wrote an article for the New York Times where he claimed to have developed a new bomber which he dubbed the Battlecruiser. The European allies were apparently so impressed that they had already ordered 11 examples of the battlecruiser by the time of his article's printing. There was just one small, inescapable error in this article. The plane didn't actually exist, and I imagine there would have been some incredulous remarks in British and French aviation circles when a copy of this article finally reached their offices. Realizing that backing up his claims and actually developing a feasible heavy bomber was probably beyond him, Christmas set his sights on a more modest goal, and that was to build a fast, single-seat biplane, which sounded normal enough. Until he began trying to convince his management and the army that his plane was the perfect tool for a daring mission to kidnap Kaiser Wilhelm II. I wish I was making this up. Incredibly, despite having no physical evidence of previous aircraft designs, or any formal qualifications outside of medicine, and even here something that might be somewhat inflated, Christmas managed to enlist the required help to build his Kaiser kidnapping contraption. Firstly, he managed to find a brokerage to invest in his project. Secondly, he convinced the near-bankrupt Continental Aircraft Company to build the plane. And thirdly, he managed to convince a senator to approach the army about securing a powerful engine, which was a difficult thing to come by during wartime. For the project to have even made it this far, all parties concerned must have been colorblind, otherwise they could not have missed the sheer quantity of red flags that were presented with such an endeavour. Christmas never put his full aircraft specification to paper, but it was so bizarre that it almost made the workers at Continental Aircraft pull out from the deal, had they not been so desperate for money. It was to be built as an unequal span biplane, however its wings had no struts, nor any wire bracing to hold them together. With his superior knowledge on aircraft design, Christmas believed that the wings should be flexible, and that they should flap like a bird's. The main method of control would be wing warping, something designed and patented by the Wright brothers, and indeed a somewhat common sight amongst early aircraft designs. But how this was expected to work on such unconventional wings was anybody's guess. The materials used to construct the plane were not always the types found on aircraft at the time, and Vincent Bernelli, the chief engineer at Continental Aircraft, made multiple public statements to the fact that he was only involved with the design of the fuselage. Privately, he had grave concerns about the design. The tail surfaces were too small, the materials used were subpar, and the wings were so heavy that they had to be winched in place during construction. But Christmas ignored his pleas, and Bernelli eventually resigned from Continental over his concerns about the safety of the design in general. By the time everything was finished, the war was over, and as such, the Kaiser was no longer the most ideal target for a political kidnapping, but that did not deter Dr. Christmas. During the later stages of construction, the aircraft had been given the nickname of Bullet, for whatever reason, and it was given an engine in the form of a US Army Liberty 6. The Army had agreed to fitting the engine to Christmas's design, but only on the provision that it be used for ground testing, and that Army officials had to be present for the first flight. Of course, these words fell on totally deaf ears, and Christmas immediately began searching for a test pilot. Strangely enough, many were reluctant to get into a plane that had a fuselage built from hardwood and steel, but had wings that looked about as strong as a piece of damp cardboard. And it was not until the end of the year that Christmas finally found a gullible enough pilot to shoehorn into his plane. Cuthbert Mills, a pilot with the Air Mail Service, took the Christmas Bullet up for its first, and only flight. After climbing for some time, the wings, which were designed to flap like those of a bird, decided instead to simply break off from the Bullet, and the plane plummeted to the ground, taking Cuthbert Mills to his death. The accident did not deter Christmas in the slightest. In fact, he covered up the whole thing, and claimed that Mills had successfully completed the test flight. He immediately began work on a second Christmas Bullet. However, he had to source a different engine, as he had not even bothered to tell the Army that A, the plane had failed, or B, their engine had been destroyed during said failure. In March 1919, Christmas put the second Bullet on display at the New York Air Show, where he had the audacity to advertise it as the safest, easiest to control plane in the world. It was this safe, easy-to-control plane that flew later on in that year, and much like the first, its wings promptly snapped off from the fuselage, and the resulting crash once again killed another pilot. After this, there was no more interest from the US Army in Christmas's design, surprisingly, but he also faced no consequences for his duplicitous actions. Not only that, but he continued to push for the development of his revolutionary designs, even attempting to go before Congress and claiming that he was swamped by orders from Europe for the bullet, and that his plane was capable of 200 miles an hour and more. Perhaps the most ridiculous part of this story was that he actually got paid by the Army, who had previously agreed to buy his so-called flexible wing design. In 1923, Christmas finally sent the Army a bill for $100,000, and the Army paid it. He passed away in 1960, a relatively wealthy man, and the Christmas bullet would go down as one of the most ludicrous aircraft in history.
Episode 8, The Stipa Caproni.
On October the 7th, 1932, a highly experimental aircraft prepared for its first flight. This was the Stipa Caproni, or the Caproni Stipa, depending on who you talk to. It was designed by Luigi Stipa and built by Giovanni Caproni's aircraft company. Though it may have looked like the strange love child of a GB racer and a dustbin, it was in fact an innovative design that, despite appearances, was completely flyable and represented an early example of ducted fan technology. In the early 1930s, the Italian fascist government wanted to showcase the success of Italian technology, and in particular, they wanted to show off their best advances in the field of aviation, a topic of international prestige. Italy had already achieved notable success with commercial aircraft, such as the Savoia Marchetti S-55. But the Air Ministry wanted something that was cutting edge, something that had not been attempted before, and thus their attention was quickly caught by a radical new design submitted by Luigi Stipa. Born in 1900, Luigi Stipa was interested in engineering from a young age. Unfortunately, the First World War interrupted his education, and he spent the latter years of the war serving as a sharpshooter. Following this, he returned to his education and spent the post-war years earning academic degrees in aeronautical, hydraulic, and civil engineering. He then found himself a job with the Italian Air Ministry, where he worked his way up to the position of General Inspector of the Engineering Division. During the mid to late 1920s, he began to work on several theories for making aircraft more efficient. As a hydraulic engineer, he knew that the velocity of a fluid increased as the diameter of the tube through which it passed narrowed. Called Bernoulli's principle, the relationship between the velocity and the pipe diameter was a well-understood axiom of fluid dynamics by the 1920s. Applying Bernoulli's principle to airflow, Stipa believed he could increase the efficiency of an aircraft's engine by directing the prop wash through a venturi tube. Stipa called his concept an in-tubed propeller. He designed, built, and tested several aircraft models that featured this new concept, and after multiple iterations had gone through rigorous wind tunnel experiments, Stipa believed he had worked out the optimum shapes which the propeller and tube would be designed to. As it turned out, the optimal shape for the tube's inner surface turned out to be almost exactly identical to that of an aerofoil, and so in many ways, the tubular fuselage of his design essentially resembled that of a wing that had been rolled up into a tubular shape. Stipa published his findings in the Revista Aeronautica, along with design drawings for a single-engine test aircraft. He then approached his superiors at the Air Ministry about the possibility of building his plane, and the Minister for Aeronautics, keen to showcase new innovations, almost immediately agreed. The decision was made to build a small aircraft that was to be powered by a 120 horsepower engine. This was not the ideal outcome for the realization of the design, but rather it represented a compromise. Firstly, building a smaller aircraft would of course save money, and if the endeavour turned out to be a failure, then the loss would be reduced. And secondly, there had been no major wind tunnel tests done on larger complete models, and so there was no data available to determine the maneuverability, aerodynamics, and general behaviour of a larger design. However, on the flip side, it was acknowledged that Stipa's design was written out with larger aircraft in mind, and indeed it was considered poorly suited for smaller ones. But with the ministry reluctant to finance a larger project, for the reasons mentioned just before, Luigi Stipa had to make do with what he had. Eventually, he came to an agreement with the Air Ministry, and they contracted the Caproni Aviation Company to construct the experimental prototype. As regular viewers of this channel already know, Count Gianni Caproni was no stranger to experimental designs. You only have to look at the CA-60 Novaplano or the CA-90 to get clear evidence of that. And as a result of these adventurous designs, his company was probably the most qualified in Italy to take on the challenge of realizing Stipa's theory. In terms of its construction, the aircraft in general was rather simple, but it featured some notable changes from the wind tunnel models that I will cover shortly. As mentioned earlier, the tubular fuselage resembled a wing that had been rolled up, and as such its construction closely resembled that of normal wings as well. It had two strong main rings, which could be considered large circular spars. On these spars were mounted longitudinal ribs, which were similar in design to wing ribs, and these were braced by a series of smaller spars, which were again circular like the main ones. The elliptical wings looked almost comically flimsy, but that was only a visual effect courtesy of the fuselage's size. These wings were built in the traditional manner, being made of wood with a fabric covering, and to improve strength, the wing spars ran along almost the entire span, passing through both the tubular fuselage and the engine nacelle itself. At the rear, the rudder and horizontal stabilizers were mounted onto the trailing edge of the fuselage. It was hoped that by placing the rudder and elevator in the path of the air pushed back by the propeller, they would allow a superior level of control, and so in turn the size of the control surfaces could be reduced. In the end, this reduction would never take place, and in fact it would be later suggested that their size be increased rather than decreased. The 120 horsepower engine took the form of the 4-cylinder de Havilland Gypsy 3. This drove the so-called in-tube propeller, which was a two-blade fixed-pitch wooden unit that fit snugly within the dimensions of the fuselage. This engine was supported by a frame that was connected, along with the wing spars, to the main circular spars of the fuselage. When first completed, the engine was housed in a small nacelle. However, there is evidence that this was removed on multiple occasions, though it is unclear if this was to test the effects of the aircraft's handling, or if this was due to some sort of heating or cooling issue. Now, I mentioned earlier that the prototype featured several differences compared to the original wind tunnel models. Some of these differences are worth noting as they directly impacted the performance of the aircraft. Firstly, to simplify the construction, the tubular fuselage was redesigned to be symmetrical. In Stipa's original design, the fuselage was dissymmetrical so that it could generate a certain amount of lift, even at zero angle of attack. But with the new changes, this lift was reduced, while at the same time overall drag increased. Secondly, the wings were braced by 4 steel wires, whereas on the original wind tunnel model, this was not the case. It's unclear whether this was an oversight by Luigi Stipa, or whether it was the result of further investigations that deemed it necessary to reinforce the wings in this way. Regardless of the decision, this, and the changes to the fuselage, affected the overall drag, which meant that the estimated top speed, climb rate, and general handling characteristics of the aircraft would not match the predictions of the earlier wind tunnel tests. But even with the negative effects of these modifications, the plane was expected to be perfectly airworthy, and so construction continued as planned. For those who first gazed upon it, it must have been a rather strange sight, and while Caproni was silently adding another sticker to his weird aircraft design bingo card, the tubular plane was made ready for its first test flights. The date of the first flight was October 7th, 1932. And despite some suspicious glances from onlookers, the pilot already had some praise for it before it even left the ground. Since the propeller diameter was the same as that of the fuselage, the Stipa Caproni sat very low to the ground, and thanks to a fairly wide undercarriage, this meant that it had excellent ground handling characteristics. That being said, it did look rather comical when it was being taxied around the airfield before taking off. Flying the aircraft was Caproni test pilot Domenico Antonini, a veteran test pilot who had flown many of Caproni's more bizarre designs, such as the huge CA-90 biplane, for example. After pottering around the airfield to get a feel for the engine and the throttle, Antonini powered up and the barrel-like plane took off for the first time. Overall, the aircraft behaved well in the air, and Antonini found it easy to handle. Following the first successful flight, a series of test flights were conducted to gather data and evaluate the soundness of Luigi Stipa's theory. These first tests did indeed confirm that the design seemed to make more efficient use of the engine compared to a more conventional design. Though the redesign of the fuselage had reduced the additional lift it provided, it still created enough that it had a superior climb rate over a conventional aircraft with the same engine, and it also had a very low takeoff and landing speed of just 68 km an hour. It was also incredibly stable. In fact, it was sometimes too stable, with subsequent test pilots complaining that it was difficult to pull the aircraft into banked turns. What was unknown to both Stipa and Caproni at the time, but was later revealed by further testing, was that the tubular fuselage generated far more lift than expected. As such, the required wing area for stable flight was less than what was designed, and had further models been built, the overall wing size could have been much smaller. Although the design increased the efficiency of the aircraft, in terms of engine power required for lift, the design also created so much drag that it essentially cancelled out any of its benefits. As a result of this, the aircraft was slower than expected, reaching a top speed of just 131 km an hour, with the engine threatening disintegration if it was pushed any further. Some of this aerodynamic drag was created by the modifications made during construction, but some of it was created by the in-tubed propeller design in general. Ultimately, the low-powered engine and bulky propeller were not enough to take advantage of Bernoulli's principle and generate superior thrust. And so when the aircraft was handed over to the Regia Aeronautica for testing, it failed to outperform conventional designs. Though it was reviewed favourably by Air Force test pilots, the decision was made to cancel further development, and no additional prototypes were built. This was a huge disappointment to Stipa, and Caproni as well, who had come to appreciate the potential of the design. Stipa had designed and built several models for larger aircraft, specifically flying wings equipped with 2 or 4 in-tubed propellers, and they tried to secure funding for a new project. However, these attempts ultimately failed. Had a larger prototype been built, it could well have been very easy to fly, if the Stipa Caproni was anything to go by, but this flight of fancy would never come to pass. Though the Air Ministry didn't embrace Stipa's design, it didn't stop them and the Italian government from using it as a propaganda tool. Stipa patented his in-tubed propeller design in Germany and in the United States, and his work was published in multiple countries. In fact, a large amount of my source material comes from a NACA technical memorandum that was written up in 1934. Unfortunately, this remarkable aircraft was eventually scrapped, but a 3:5 scale replica was built in Australia in the 1990s. It was built by Lynette Zaccoli and Aerotech Queensland, and it made at least 2 flights in 2001. It's unclear if the replica was ever flown again after this, but it can be found on display at the Toowoomba airfield, which is not too far away from where I live, so maybe I'll do a follow-up video where I go and pay it a visit. Although Italy made no further efforts to develop Stipa's design, a more advanced derivative would be realised in 1940. Though the Caproni Campini N1 was nowhere near efficient enough to be practical, it did make use of a ducted fan compressor buried in the fuselage, and by adding additional fuel to a combustion chamber in the tail, it gave Italy the laudable claim of producing the world's first afterburning aircraft. But that's a story for another day.
Episode 9. The Curtiss SO3C Seamew.
Recently, we looked at the Curtiss SOC Seagull, and today we're taking a look at the plane that was designed to replace it, but ultimately failed to do so, the SO3C Seamew.
Development work on the Seamew began in 1937. At the start of the year, Curtiss and Vought, the US Navy's main supplier of catapult scout planes, were approached to submit designs for a high-speed replacement of the SOC Seagull. The naval specification called for a mid-wing monoplane with a crew of 2, a pilot and an observer. It required the design to feature a removable centerline float, one that could easily be replaced with a fuselage-mounted landing gear for land-based operations, and it also required that the wings had to be able to be folded back due to the deck and hangar space limitations aboard battleships and cruisers. All of this had to be built within a weight limitation of 6,350 pounds. However, the most stringent and critical part of the design specification was the engine. The Navy wanted to use a new, experimental, and mostly unproven engine for this new Scout. This was an air-cooled 12.7-litre inverted V12 being developed by Ranger. It boasted a very low fuel consumption, and this greatly interested the Navy, as it meant they could increase the range of their scout planes without hampering their performance by adding additional fuel tanks. Unfortunately, this engine would prove to be the equivalent of an Achilles heel for the Curtiss Seamew, though of course they didn't know it at the time. Curtiss submitted their design to the US Navy in August of 1937, and in May of 1938 they were awarded a contract to produce a prototype that would be designated as the XSO3 C1. At the same time, Vought also received a contract to produce a prototype, the XSO2U1, and the two planes would be evaluated against each other. In its original form, the Curtiss prototype could be considered fairly good-looking. Unlike its predecessor, the SOC Seagull, it was an all-metal design, ditching the fabric-covered fuselage and wings for stressed aluminium paneling. Similar to other Curtiss monoplanes, the wing leading edge was straight, whereas the trailing edge tapered towards the wingtips. The two most recognizable features were the engine's exhaust stacks, which protruded out from the bottom of the nose, and the flush line of the upper fuselage that ran from the pilot's cockpit all the way back to the tail. The prototype aircraft was complete by the autumn of 1939, being initially fitted with a fixed landing gear, and it flew for the first time on the 6th of October. After this, it went on to compete in a series of competitive trials against the prototype submitted by Vought. Due to the strict requirement of the naval specification, both planes looked remarkably similar, and as such, their performance figures were also very close. Though the Vought design was 3 miles an hour faster, it was also over 300 pounds heavier than the Curtiss, and after due consideration after the trials, the decision was made to go with the Curtiss design. An initial production order of 300 units was placed, but before the first aircraft even left the factory, there were some worrying signs that not all would be well. In March 1940, Curtiss gave the original prototype to the Navy for its final trials. Cooling and stability problems plagued these trials from the outset, and indeed there had been a few worrying signs in the earlier trials with both the Curtiss and the Vought prototypes. Early on in these final tests, the engine overheated so badly that it completely failed, causing the prototype to sink in shallow water on the 21st of July 1941. Curtiss took it back to their production facility at Buffalo for a rebuild, but the engine failed again later on in November. Unwilling to produce 300 versions of an aircraft that A. suffered in lateral stability, and B. had an engine that was so fragile it might as well have been a glider, Curtiss sent the prototype to Langley Field to undergo a series of wind tunnel experiments to sort out the problems. Based on their findings, Curtiss enlarged the air intake and added extra cowl flaps, and while this didn't completely solve the heating issue, it did reduce it to the point that the engine wouldn't try to explode if the pilots looked at the throttle. The issue of stability was solved by a series of iterative changes that didn't happen all at once, but they ultimately resulted in the enlargement of the tail surfaces and rudder, the addition of a dorsal fin section that ran aft of the cockpit, and the addition of upswept wingtips. When the SO3C finally entered production, it was given the name Seamew by Curtiss, but the US Navy named it the Seagull in 1941, which was the same name as its predecessor. However, despite being built later, it was in fact the first to be given this name, as the US Navy retroactively named the SOC as the Seagull when they were brought back into frontline service, an embarrassing topic that we will cover shortly. As a result of this, the SO3C is both known as the Seagull and the Seamew, but I always refer to it as the Seamew to prevent unnecessary confusion. It was built in 3 main variants, with a few single outliers. Of the initial production order for over 300 units, 141 would be completed as the SO3C1, with the first of these aircraft being delivered in July of 1942. As a scout plane, its armament was light, a single forward-firing 30 caliber machine gun in the nose, and a rear-mounted 50 caliber machine gun for defense. It also had a set of wing racks that allowed it to carry a pair of 100-pound bombs. Potentially, it could also have carried a pair of depth charges as well, but I couldn't find exact numbers on this for the first production model. The second production model, the SO3C2, definitely could carry depth charges though, and they also came with a ventral bomb rack. The other main differences included the fitting of an arrestor gear for carrier use, and the fitting of an uprated version of the Ranger engine that now put out 520 horsepower. Approximately 200 of these second versions were built, making them the most numerous of the US models. After this, there were plans to build almost 700 of the SO3C3, but very few of these last models were actually built as the aircraft was being hastily withdrawn from service due to it being somewhat of a colossal failure. Though the heating and stability issues on the prototype had been fixed, once the production Seamews entered service with US fleets, a myriad of other problems quickly became apparent. The largest and most embarrassing of these was the inability of the Seamew to make a water takeoff with a full fuel load. Now, admittedly, this was only partly the fault of the aircraft, as the Navy had also stipulated increased fuel load requirements. But regardless of this, it meant that the Seamew could only take off from the water with less than half of its maximum fuel load aboard, which for a scout plane that needed long range was hardly ideal. Along with that particular issue, 2 other problems arose that made it vastly unpopular with the officers who had to fly it. Firstly, it was discovered that in rough water, the central float flexed so much that the propeller could actually strike it. This was unfortunate for several reasons. It damaged the propeller, it damaged the float, and it terrified the pilot. Secondly, the takeoff attitude from the water was alarmingly steep, to the point where there was a brief moment of time where the Seamew would have no aileron control, and the pilots had to bring the tail up as fast as possible to maintain any control at all. This also meant that if a problem occurred, or if a strong wind gust forced a stall, there was zero hope of recovery. These problems, and a series of excessive operational accidents, quickly resulted in the early withdrawal of the Seamew from service. It was then supplemented by the very plane it had been built to replace, the SOC, which quickly took on the Seamew's naval designation of Seagull for itself. In the end, the Seamew was such a failure that the average length of time that it was used on each of its assigned ships was just about 2 months. Following this, the Navy tried to find use for the Seamew as a radio-controlled target tug, and these were redesignated as the SO3CK. This didn't last long, as they lacked the engine power for this sort of role, and they were rarely used. A number of the SO3Cs were ordered by the British Royal Navy under the terms of the Lend-Lease, and these would officially be known as the Seamew rather than the Seagull when in service with the fleet's air arm. These units were delivered with a fixed landing gear, an arrestor hook, and a central bomb rack. However, like their American counterparts, these planes were quickly disliked and discarded by British pilots, who referred to them as the Sea Cow, and most of the 250 aircraft delivered to the British ended up in Canada as target tugs. There is a famous quote about the Seamew that came from a British pilot by the name of Eleanor Lettice Curtis, and her words sum it up best. It is hard to imagine how, even in wartime, such an aircraft could have been accepted from the factory, let alone given valuable cargo space across the Atlantic. Harsh words indeed. But although it was a failure, the Seamew shouldn't be considered a failure of Curtis itself. Rather, it was the failure of an experimental engine, the failure of overly strict naval specifications,
and then the failure of said Navy to comprehend the consequences of changing the specifications after the aircraft had entered production. All of this would be proven by the Seamew's replacement, the Curtiss SC Seahawk, a plane that wasn't hampered by design restrictions or an untested experimental engine. But that's a story for another day.
Episode 10. The Gloster F.5 34.
In the mid-1930s, the RAF was in need of a newer, more advanced single-seat fighter to replace their aging fleet of biplanes. In response to this need, the Air Ministry issued Specification F5/34. Several manufacturers submitted designs. Some would make it, some didn't, and they will all be covered in their own videos. But today, we're looking at the submission by Gloster. This new specification, which would ultimately lead to the Hawker Hurricane and Supermarine Spitfire, was a considerable step up in design requirements in comparison to previous specifications. The new fighter had to come with a fully retractable undercarriage, it had to possess a top speed of 275 miles an hour, or 442 kilometers an hour, at 15,000 feet, it had to have a fully enclosed cockpit with an oxygen supply, and it had to come with 6 or 8 .303 Browning machine guns with 300 rounds of ammunition each. These high-performance requirements would prove a challenging but not impossible obstacle to overcome, at least for designers who were not doggedly stuck in the past, and when approached with the Air Ministry's specification, Gloster was quietly confident, owing to the successes of the Gloster Gladiator. Known unofficially as the Gloster Unnamed Fighter, the F-534 would be the last aircraft designed for the company by H.P. Folland, who left after Hawker's acquisition of the company in 1937. Interestingly, the Air Ministry specification did not dictate a particular type of power plant that was to be used, something which had hurt several promising designs in the past, and so Folland decided to go with an air-cooled radial engine on the grounds of reliability. Folland collaborated with H.E. Preston on the design of this new fighter. Initially, the aircraft had a more primitive design compared to what would eventually be built. Leaning heavily on the design principles of the Gloster Gladiator, its fuselage would have been clad in fabric, and it would have only featured a partially enclosed cockpit, which had a detachable overhead fairing with open sides. The power plant originally selected was the relatively new 9-cylinder Bristol Perseus sleeve valve radial engine, but by 1936, several major design changes had been made to improve Gloster's competitiveness, and this also included a change of engine. In the redesign, Folland went with a geared, supercharged Bristol Mercury 9 that produced 840 horsepower. This was done due to concerns about the reliability of the still somewhat experimental Perseus engine, and as the Bristol Mercury had seen stunning success with the Gloster Gladiator, Folland chose to play it safe. The Mercury was enclosed in a new long-cord cowling with a leading-edge exhaust collector ring, and to improve cooling over the original design, it also had controllable cowl flaps. The fuselage was a monocoque structure that was built up from oval section rings. The fabric coverings were done away with in the redesign, and the Gloster was now to be clad in a stressed duraluminum skin. The wing was built in one piece, with the light alloy spars running from tip to tip, and the ribs were made from steel and light alloy tubing. Like the fuselage, the wings and tailplane were also covered in a stressed metal skin, and the ailerons, rudder, and elevators were clad in fabric. The aircraft also featured split trailing edge flaps, however these were built with an all-metal construction, and like most emerging designs at the time, they were hydraulically powered. Another noticeable change in the redesign was the canopy, which now closely resembled that of the Gloster Gladiator, being fully enclosed and retractable. It also offered superior all-round visibility compared to the previous design, as the original had its canopy faired into the fuselage. Though it looked like a conventional design, in the way that we now perceive early monoplane fighters, the F-534 did feature a couple of oddities. Firstly, there was the design of the landing gear. Though it was retractable, it was not fully retractable. The main wheel retracted rearwards into the wing, but a large section of it was left exposed. This was done so that in the event of a wheels-up landing, the main point of impact would be the wheels rather than the underside of the airframe. Though this sounded like a potentially cost-saving strategy, and indeed a few other manufacturers tried this technique, it would ultimately prove to be a brief and rarely used design feature, as the benefits of only somewhat reducing the damage of a potential wheels-up landing were vastly outweighed by the increased drag produced during every flight, irrespective of the chances of said wheels-up landing even occurring. The second design oddity was the tail. In the redesign, a new tail unit was adopted, in which the tail fin and rudder were set further forward than the tailplane and elevator. This was done to aid in spin recovery, a topic that was rapidly evolving with the change from biplane to monoplane designs, and it was hoped that spin recovery would be improved by moving the rudder ahead of any disturbed air caused by the tailplane. Again, this would be a design feature on a few other aircrafts as well, but for one reason or another, it never took off. Pun fully intended. The updated design submitted by Gloster resulted in the production of two prototypes. The first was built as an unarmed model, and it was flown for the first time in December of 1937. The second, completed with a full complement of 8 machine guns, was flown for the first time in March of 1938. Like the other competing prototypes, the aircraft's armament was mounted in the wing, outboard of the propeller disc. This eliminated the requirement for a heavy and complex synchronization gear, and it took full advantage of the growing reliability of remotely operated machine guns. During its initial trials, the Gloster prototype performed well. In fact, it managed an almost identical top speed compared to the Hawker Hurricane, despite having approximately 100 horsepower less than its competitor. But overall, the Gloster prototype was doomed, and this was for two main reasons. Reason 1. The Gloster may have performed well compared to the Hurricane overall, but its Bristol Mercury engine was reaching the end of its development potential, whereas the Merlin engine was only at the beginning of its own. This meant that when a replacement for the Mercury engine would eventually be needed, Gloster would be limited in their engine choices, as anything with dimensions or cooling requirements dissimilar to the Mercury would more than likely require a major redesign. The other reason for Gloster's failure was, ironically, their earlier successes. Much of their development and production capacity was taken up with existing orders for Gloster Gladiators and Gauntlets, and this meant that they had limited resources to spare on a new project. And so, despite being structurally more advanced than the Hurricane, the Gloster prototypes were so slow in development that they only began performance trials when the Hurricane itself was already entering service. There was definitely room for improvement to bring the Gloster up to a more modern specification. Its airframe could easily bear the fitting of a more powerful engine, albeit with some redesign work on the nose, and the wing-mounted machine guns could have easily been swapped out for cannons later on. But the Air Ministry saw zero reason for wasting money on either of these endeavours when the Spitfire and Hurricane were already fulfilling their roles to admiration. And so, only 2 examples of Gloster's unnamed fighter would be built. After completing their flight trials, they were transferred to the Air Ministry for use at RAE Farnborough and various other establishments. This they did until around May of 1941, when they were then transferred for use as ground instructional airframes, and at some point later on they were both scrapped. Though the project was not a success for Gloster, their takeover by Hawker in 1937 would breathe new life and new ideas into the company. However, this turn of events did not please Folland, who felt that the new owners would favour the designs of Hawker's own Sydney Cam over his. When Folland resigned to form his own company, he was replaced by W.G. Carter, who would go on to design the company's most well-remembered aircraft, the Gloster Meteor. But that's a story for another day.
Episode 11. The de Havilland DH-108 Swallow.
Today, we're taking a look at the de Havilland DH-108 Swallow, a plane that was as innovative as it was dangerous. It was a supersonic jet that did much for the development of Cold War aircraft in Great Britain. In fact, it was the first British jet to break the sound barrier, but its tragic history has often overshadowed its accomplishments. The development of the Swallow can be traced back to the Second World War. As early as 1942, steps were being taken to ensure that the British aircraft industry, which had grown considerably during the war, would still have a good supply of work, and thus maintain a large number of jobs, once the war was over. This resulted in the formation of the Brabazon Committee, the goal of which was to investigate the needs of a post-war civil airline market in both Britain, its overseas territories, and the Commonwealth in general. Eventually, the first, and then the second Brabazon Committee would culminate in the drawing up of specifications for the construction of 7 new aircraft designs after the war. The Brabazon Committee is a complicated and deeply interesting topic, at least as far as aviation is concerned, and it's definitely something that will be covered in its own video, but for now we will only focus on the bit that affects today's featured aircraft. The Type 4 aircraft specification from the committee was the most advanced, and it called for the design and construction of the world's first jet airliner, which would eventually evolve into the DH-106 Comet. In the earliest stages of the design process, the 106 was originally intended to be a tailless aircraft. The concept of the original design was so advanced that de Havilland had to design and develop both the airframe and the engines, and it was the development of the airframe that led to the DH-108. Unsurprisingly, de Havilland was reluctant to stick 36 passengers in such a radically new design without prior experimentation, and so, in October of 1945, a scale model of the design was ordered, one that would be used for testing to find any potential problems with aerodynamics, hull stresses, and to learn some of the techniques required for high-speed jet-powered flight. The result was the DH-108, and this mini-comet was given the unofficial nickname of Swallow. The development of the Swallow was covered under Air Ministry Specification E18/45, which was drawn up in January of 1946. This required the construction of 2 airframes for conducting full-scale experiments on high-speed flights with swept-back wings, to evaluate aerodynamic and structural forces experienced during high-speed flight, and to act as an approximately half-scale version of the proposed multi-engine jet airliner that would become the Comet. De Havilland designer John Frost was put in charge of the project. By this point, he had gained valuable experience in the design and production of jet aircraft, having worked on the team that developed Britain's second jet-powered fighter, the DH-100 Vampire. As this aircraft was already tried and tested, the Swallow was directly developed from it. It made use of the fuselage and power plant of the Mark I version of the Vampire, the power plant being a de Havilland Goblin II, the tail booms were removed, and the wings were replaced with ones that had a sweepback of 43 degrees. The 2 Swallows ordered under the specification were built from 2 existing Vampire airframes. These were being built on the production line operated by English Electric. The first airframe was given the new registration of TG-283, and the second was given TG-306. But to save me repeating serials half a dozen times in a 5-minute window, I shall simply refer to them as Swallow 1 and Swallow 2. After being delivered to Hatfield in September of 1945, work on converting Swallow 1 from a regular Vampire into its experimental layout began. The original Vampire fuselage pod was extended rearwards to make room for the vertical fin. The pod had been built in wood, but the new additions to the airframe, the rear fuselage and the fins, were all made from light alloys. The swept wing used a main spar plus auxiliary front and rear spars, and it also housed extra fuel tanks to offset the change in dimensions affecting the fuel consumption. Swallow 1 was designed to investigate low-speed handling. For this, it had wooden Handley page slats that ran the full span of the wing leading edge and over the air intakes. This restricted its maximum airspeed to approximately 280 miles an hour, or 450 kilometers an hour, though some sources conflict and claim it could actually go as fast as 350 miles an hour. As it was designed to test stalling, the risk of uncontrolled spinning was duly appreciated. Special anti-spin parachutes were installed to combat this, being fitted to the wingtips, though as we will see later on, their effectiveness was questionable. The second Swallow also had slats built into the wings, but these were retractable and operated automatically as a safety feature, as this aircraft was designed for high-speed testing. Converting the aircraft from Vampires to their experimental specifications was completed in rapid time, and on the 15th of May 1946, Swallow 1 flew for the first time, taking off from a secluded airfield at Woodbridge with Geoffrey de Havilland Jr. at the controls. After proving that the hastily converted Vampire could indeed fly, it was then taken to Hatfield for manufacturer trials. Not long after this, the second Swallow was ready for its first flights as well. It first flew as a normal de Havilland Vampire in February of 1946, but that was only to take it to Hatfield for its conversion works. After these were complete, again, done in a record time that probably should have raised several safety concerns, it took off in its experimental swept-wing form in June. This aircraft was used to assess the high-speed characteristics of the swept wings, and during its initial trials, progress was rapid, though not without some concern. In many flights, the pilots began to encounter compressibility at airspeeds of 340 miles an hour at 35,000 feet, which resulted in a phenomena known as Mach tuck. This was a tendency for the nose to pitch down as the plane approached its critical Mach number. This was not unexpected, and with pitch correction, the pilots found it relatively easy to maintain control. However, the aircraft was only put near its critical Mach number at higher altitudes, as it was thought that the pitch oscillation caused by Mach tuck would be increased at lower altitudes where the air was denser. As the tests continued, the high-speed performance of the second Swallow began to exceed expectations, so much so that it was decided to have a go at breaking the world airspeed record, which was currently held by a Gloster Meteor that clocked in at 616 miles an hour or 991 kilometers an hour. And this is where the Swallow's story begins to turn sour. On the evening of the 27th of September, during one of the trial flights made in preparation for the record attempt, Geoffrey de Havilland Jr., who was flying the Swallow high over the Thames estuary, took the plane into a shallow dive from 10,000 feet. During this dive, the Swallow reached an estimated speed of Mach 0.87, and it was here that it suffered a violent pitch oscillation that caused the aircraft's wing spars to crack and fail at the roots, which of course led to the wings folding back as if they had been snapped like those off a toy in the hands of a heavily handed child. I talked about critical Mach in our recent video on the Bell X-1. What happened here was that the air flowing directly over the wing was already at supersonic speeds, even though the plane was not. The shockwave caused by this forced the airflow away from the control surfaces, which at first reduced the effectiveness of the elevators. Then it went on to cause a reversal of pitch, a nose-down change in trim, and a severe reduction of longitudinal control. All of this culminated in the destruction of both the aircraft and the death of de Havilland Jr., which was a tragic loss for the company. The exact cause of the crash was not known until extensive wind tunnel tests on several models gave the full picture. However, despite the loss, the value of the second Swallow as a high-speed aircraft had been established, and a third prototype was ordered and completed, being registered as VW-120, but I shall just refer to it as the Swallow 3. This model featured several major changes over the first two Swallows. It had a more pointed nose, a stronger airframe, reinforced wing roots, for obvious reasons, a more powerful Goblin 4 engine, powered control surfaces, and fully automatic leading-edge slats. This sleeker, more aggressive-looking Swallow flew for the first time on the 24th of July 1947. It made its public debut at the SBAC Airshow at Radlett in September of the same year, and following this, it was put into a series of high-speed trials, as well as entering for several speed record attempts, of which on the 12th of April 1948, it set a new 100-kilometer closed-circuit speed record with an average speed of 605 miles an hour. However, there were still some problems. Flights at high speed and altitude revealed a loss of roll control at Mach 0.99 and a severe reduction of pitch control at Mach 0.97. Eager to avoid another public tragedy, de Havilland imposed Mach limits on the aircraft until it could engineer a solution. These limits appear to have been completely ignored when, on the 6th of September 1948, test pilot John Derry put the aircraft in a dive from 45,000 feet. During this dive, the aforementioned control issues made their appearance, and he lost control, though thankfully he was able to regain control again at 23,000 feet. During this chaotic descent, a speed of between Mach 1.02 and Mach 1.04 was recorded, which meant that the DH-108 Swallow had become the first British aircraft to break the sound barrier, albeit whilst out of control. Not long after this, it then became the first British aircraft to go supersonic while under actual pilot control, as well as being the first supersonic plane in the world that could take off and land under its own power. The Bell X-1 may have broken the sound barrier first, but it was air-launched to save fuel. On the 11th and 12th of December that year, the record-breaking plane was displayed to the public at the Farnborough Air Show, and then the following year it went to the Royal Aircraft Establishment to join the first Swallow, which had been quietly completing its slow-speed handling tests. Those who flew the Swallows almost unanimously found them to be difficult to control, bordering the line of being too dangerous in general to even consider flying. One of the test pilots who flew the third Swallow, Captain Eric Brown, was severely critical of its handling. It had a nasty tendency to stall suddenly, catching out even the most experienced pilots, and its tendency to oscillate violently at high speeds caused him to label the aircraft as a killer. His words would turn out to be prophetic. On the 15th of February 1950, the third Swallow crashed at Brick Hill near Bletchley after the test pilot, squadron leader Stuart Muller-Rowland, lost control. The aircraft had performed a high-speed descent from 27,000 feet, and it had broken up below 10,000 feet. Witnesses recall it spinning violently out of control, one wing having snapped off, before crashing into a wood. Initially, it had been thought that the loss of control was due to a fault in the oxygen supply system that had incapacitated the pilot, but later on further investigations pointed to a failure in the left wing spar as the ultimate cause. This left the original, and now singular, DH-108 Swallow to be used as a dedicated low-speed research aircraft. This it did for about 3 months, until it too was destroyed in an accident. During a stalling trial at 15,000 feet, the aircraft entered an uncontrolled inverted spin. The anti-spin parachutes that were meant to save it failed to function properly, and the test pilot, squadron leader George Genders, or Genders depending on how I'm meant to be pronouncing this, prepared to bail out. But at around 2,000 feet, he made a partial recovery, only to lose control again moments later. This time he did bail out, but his parachute failed to deploy due to the low altitude, and he was killed. Despite their tragic safety record, something that was not at all uncommon in those early years of high-speed jet aircraft, the de Havilland 108s achieved a number of firsts for British aviation. For Britain, they would be the first swept-wing aircraft, the first tailless jet aircraft, and the first supersonic aircraft. That being said, the loss of the second Swallow did convince de Havilland to go with a less radical design for their multi-engine jet airliner. Though, in a cruel twist of irony, the de Havilland Comet will also become infamous for its tendency to disintegrate during flight, albeit for different reasons. The man behind the ill-fated Swallow, John Frost, moved to Canada not long after he completed the initial design work in 1947, and here he would continue to work on some very interesting designs, which included the UFO-like Avrocar. But that's a story for another day.
Episode 12, The Armstrong Whitworth Atlas.
Today, we're taking a look at the Armstrong Whitworth Atlas, which was the first RAF aircraft designed specifically for the role of cooperating with troops on the ground. In the early 1920s, this sort of dedicated aircraft type didn't exist. The Army and the RAF appreciated the value of Army Corporation aircraft, not to be confused with close air support, which was more offensive in nature, but these aircraft consisted of planes that had been converted for use in this role rather than being designed for it from the outset. The mainstay of what could be considered the current Army Corporation aircraft were modified versions of the Bristol F-2B fighter and the aging Airco DH-9A. However, by the mid-1920s, things were starting to change, and the Air Ministry issued its first specification for the development of an Army Corporation aircraft. The first two specifications were 8/24 and 30/24, and these would lead to the development, or partial development, of several prototypes: the de Havilland Dingo, the de Havilland Hyena, the Vickers Vespa, and the Bristol Boarhound. There was, however, a bit of a glaring oversight with these two specifications. They did not take into account the service conditions to be found in hotter climates, particularly the Middle East, and so specification 20/25 was drawn up as a replacement. During this time, Armstrong Whitworth had begun work on a private venture aimed at meeting said new specification, but this was not the Atlas. This was in fact the almost identical-looking Armstrong Whitworth Ajax. The Atlas and the Ajax were so alike that it's easy to come to the false conclusion that the Ajax was the prototype of the Atlas, but according to Armstrong Whitworth records, this was not the case. Did the design of the former influence that of the latter? It certainly seems so, but they were not directly related. For whatever reason, only 4 examples of the Ajax would be built, and not long after construction had started on the first, work had also begun on the Atlas. The first of both the Ajax and the Atlas aircraft were completed as private ventures, and when the prototype Atlas took off for the first time on the 10th of May 1925, it did so with civil markings. The first Ajax to be complete took to the skies not long after this, and it was quickly followed by a second. Of these two, the first would go on to feature publicly at the 1926 Paris Air Show, and the second would be used as a testing aircraft. 2 further Ajax models were built not long after this, and these would be listed on company record as development for a so-called day bomber rather than an Army Corporation aircraft. That role had been passed on to the Atlas, and not much is known of the Ajax apart from this. By this point, the Air Ministry had modified their specification to accommodate updates in competing aircraft designs, and specification 3326 would see the Atlas compete against the Bristol Boarhound and the Vickers Vespa. The Atlas was built in the traditional manner, the design calling for no real innovations. It had an all-metal fuselage structure, mainly comprised of steel tubing, which was wire-braced and had ball and socket joints between the longerons and the ends of the struts. Most of the fuselage was clad in fabric, with the exception of a small area at the front that was clad in duralumin paneling. The wings were made of wood, with the wing structure built around 2 main spars, and like the fuselage, this was also fabric-covered. The power plant selected was a 14-cylinder Armstrong Siddeley Jaguar 4C, which gave 450 horsepower, and it was expected that the plane would have a top speed of between 135 and 145 miles an hour. Compared to some other biplane designs at the time, the Atlas could be considered a little on the chunky side, but the same could also be said for the Boarhound and the Vespa, and this was to accommodate the many pieces of equipment, particularly radio, demanded by its intended role. Provision was made for the fitting of 3 different types of radio, and it also carried a hook on a long pole that was used for picking up handwritten messages that soldiers on the ground would hang from a cord suspended between 2 poles. This act became somewhat of a party trick for the Atlas, and it was something that formations of aircraft would do during the yearly RAF displays at Hendon. For reconnaissance duties, the Atlas could be outfitted with a variety of camera equipment. This was located behind the observer's cockpit, and the equipment could also be remotely controlled by the pilots if they were flying solo. The intended armament for the Atlas consisted of 2 machine guns, a fixed Vickers firing through the propeller arc, and a rear-mounted Lewis gun, as well as 4 120-pound bombs that could be carried under the wing. After its initial flights and manufacturer trials were complete, the Atlas prototype went to Martlesham Heath for official trials in November of 1925. The reports from these trials were highly favourable, stating that the aircraft was stable, had good longitudinal and lateral control, and was in general very easy to fly. There were only 2 main points of criticism. The rudder was felt to be rather heavy, and the aircraft could not be side-slipped at a steep angle. Despite these 2 issues, the report was favourable enough that the aircraft was ordered into production as the Atlas Mark I. Meanwhile, in an attempt to improve the side-slipping and rudder issues, the prototype Atlas went back for modifications that would then be immediately applied to the first batch of production models. The rudder was given a greater range of movement, and at the same time, the incidence, sweepback, and dihedral angles of the wings were increased by varying amounts. Following this, the prototype went back to Martlesham for re-evaluation, and it was immediately apparent that the changes had ruined the plane's handling capabilities. Overall, its flying qualities appeared to have deteriorated, and the aircraft was now prone to sudden stalls and wing drops. This prompted a rapid return to the production shop at Whitley for even more modifications. This time, a new all-metal wing structure was fitted, with some minor variations to the control surfaces as well, but once again, the performance results at Martlesham would be both disappointing and alarming. Not only did it continue to stall suddenly, the only warning being an incipient wing drop, but it also now displayed the highly unwelcome tendency to overbank in turns, which often led to an uncontrolled spin unless the airspeed could be maintained. All of these factors combined to make takeoff and landing an unnecessarily terrifying affair for what was meant to be a very simple aircraft to fly. And seeing as the first Atlases entered RAF service whilst these experiments were still going on, they inherited many of these problems. In the first 9 months of service, Atlases suffered 11 accidents during takeoff and landing, almost all following stalls, and 2 of these even led to fatalities. These tragic events spurred on even greater efforts to fix the issues, as the RAF was contemplating ditching the Atlas altogether, and a series of further modifications were made that brought the aircraft to an acceptable level of control and safety. Unfortunately, there is not an exact record of the modifications that were finally incorporated, but some of these involved further adjustments to the dihedral angle of the wing, the washout of the wingtips, and the fitting of automatic wingtip slats. Further modifications and testing indicate that there was still some lingering dissatisfaction about the Atlas's stalling characteristics, but the plane was no longer an accident waiting to happen, and that seemed enough to satisfy the military concerns. The first Atlases delivered to the RAF went to No. 13 Squadron for service trials, and the first units to enter service operationally joined No. 26 Squadron in the summer of 1927. Between 1927 and 1930, 4 other home-based squadrons would receive Atlases, as well as No. 208 Squadron, which was based in Egypt. In spite of the early problems and criticisms encountered at Martlesham, the Atlas redeemed itself during its service life, after a rocky start, by being safe, easy to fly, and reliable. Some models were also exported. 6 were built to order for the Royal Canadian Air Force between 1927 and 1929, and they would be joined by another 10 that were purchased later on in 1934. 2 aircraft were sold to Greece, who would also produce a cheaper version under license. 1 went to Japan, 1 to Egypt, and 14 were sold to China, the latter being the new Atlas Mark II. Making its first public appearance at the Hendon Air Show in 1932, the Atlas Mark II was offered as a multi-purpose aircraft that could be used as a two-seat day fighter, a daytime bomber, or an Army Corporation aircraft. The main changes that set it aside from the Mark I was a new set of wings, a more powerful 535 horsepower Armstrong Siddeley Panther engine, a redesigned fuselage, and a larger fixed tailfin section. Despite being an overall improvement, especially in the area of stall characteristics, the Atlas II was not taken on by the RAF, and its only export success was the order that went to China. A good part of this can be attributed to the realization that the age of the biplane was drawing to its end. Armstrong Whitworth did make attempts to market the Atlas against the monoplane. In the early 1930s, they published a brochure on the Atlas II, explaining why they believed the biplane was superior to the emerging monoplane designs, citing the compactness, maneuverability, and better stalling characteristics of biplanes. But this did little to change the situation. A one-off model, the Ares, was also built. Flying for the first time in May of 1930, it was an attempt to improve upon the Atlas with an emphasis on maintenance. It had a new wing structure featuring a Warren truss, which reduced the need for bracing wires, and the sides of the fuselage were fitted with large, easily detachable panels for easy access to the internal equipment and machinery. Though the design showed promise, there was no follow-up order, and not much else is known about this elusive plane. Though the Mark II model could be considered a bit of a bust, and the Ares didn't really result in anything, the Mark Is had a fairly long service life. Along with being used as Army Corporation aircraft, some 175 units were built as trainers, coming with a set of dual controls, and at least 2 Atlases were built as seaplanes. One of these was used by the RAF high-speed flight during their training period leading up to the 1931 Schneider Trophy race. There is also evidence of the Royal Canadian Air Force experimenting with the Atlas as a seaplane as well, which would make sense given their large coastline and multiplicity of lakes, but I couldn't find much information on that particular endeavour. The other Canadian Atlases served for a long time, and with much distinction. They made regular appearances at RCAF exercises, and they would even see limited use during the Second World War before being replaced by Westland Lysanders. After almost 15 years from the first Atlas entering service, and a production total of 478 aircraft later, the last Canadian Atlas was retired from service in 1942, thus bringing an end to many years of reliable, if unspectacular, service.
Episode 13, The Grumman FF.
Today, we're taking a look at the Grumman FF, often known as the Fifi. It was the first complete aircraft designed and built by the company, featuring several novel features for the time, and it helped to establish a fruitful relationship between Grumman and the US Navy that would last for decades to come. Development of this historical aircraft began almost by accident. As mentioned in a previous video on the Grumman JF Duck, one of the company's first contracts was to supply the US Navy with the Model A amphibian floats, the design of which had been given to Leroy Grumman by his friend and former colleague Grover Loening. During discussions of said floats, personnel from the Bureau of Aeronautics asked Grumman if they thought their retractable undercarriage design, of which was used on the Model A floats, could be adapted to work on existing carrier fighters, such as the Boeing F-4B-1, which had entered service in the summer of 1929, or the Curtiss F-8C-4, which was about to do so. Unsurprisingly, Roy Grumman and his colleagues were not keen on the idea of letting other manufacturers benefit from their design, especially as practical, reliable undercarriage of this nature was still considered cutting-edge designs for this time period. Instead of giving the Navy a direct answer, Grumman and his chief designer, Bill Schwendler, set out to design a two-seat fighter that made use of their technology. On the 10th of March 1930, barely 3 months after the company had officially been organised, and less than a month after their discussion with the Bureau of Aeronautics, Grumman submitted preliminary data on a so-called high-performance two-seat fighter. This submission was well received. The Bureau saw the merit of Grumman's design, and on the 29th of March, they formally registered their interest in a project with them. After this rapid start, and in typical bureaucratic fashion of course, things immediately slowed down. On the one hand, the US Navy opened its budget file in 1930 and were greeted with the metaphorical equivalent of a moth flying out of a poor man's wallet. And on the other hand, they had to proceed cautiously before awarding a contract to a completely new and untried manufacturer, Roy Grumman's personal reputation in the field notwithstanding. This delay, however, did have its merits. It allowed Grumman time to work on their design, and it allowed the Navy time to communicate additional requirements for said design. The aircraft that began to take clearer shape on the drawing board was a small, single-bay biplane with fabric-covered two-spar wings. Its fuselage was a semi-monocoque made from aluminium alloy, a first for US carrier aircraft, and it became characterized by a deep forward section in which the main wheels were retracted vertically. The pilot and rear gunner were seated in tandem under an enclosed canopy, still a relatively novel feature at this time, and the armament was to consist of the then standard pair of fixed forward-firing machine guns and one rear-firing machine gun on a flexible mount. All of these guns were 30 caliber Browning M2s, but there was also provision for the two forward-firing guns to be replaced by a single 50 caliber Browning M3 if called for. As adopting Grumman's design into service would introduce several features hitherto unseen on carrier aircraft, notably the retractable undercarriage and the use of aluminium alloys in the framework, and after some prodding by conservative members of the Bureau of Aeronautics, who didn't wholly believe Grumman's optimistic performance estimates, the Bureau insisted that Grumman first provide drawings for a 12:1 scale model that the Navy could build and wind tunnel test. Much to Grumman's satisfaction, and probably some internal grumbling at the Bureau, the wind tunnel tests completely validated their supposedly optimistic performance estimates, and when the Navy had finally resolved their budgetary matter, they requested Grumman to submit a quotation for the design, construction, and testing of a prototype. On the 6th of March 1931, Grumman submitted a quote for $73,975, and it was accepted on the 28th when the Navy formally ordered one XFF-1, along with reserving an option for a second prototype, which they would indeed order as the XSF-1 in June. The naval contract stipulated that the XFF-1 must have a top speed of 190 miles an hour at sea level, a service ceiling of 22,000 feet, and it had to be delivered within 200 days. The delivery date was a cause for some concern at Grumman, as they had a workforce of less than 30, and they also had to waste some of those precious days relocating from their current facility, an oversized rented garage, to something more spacious. Their concerns turned out to be unnecessary, for although their prototype was delivered 76 days behind schedule in 1931, their only competitor for a two-seat carrier fighter, the open cockpit, fixed landing gear Berliner Joyce XF-2J1, wasn't delivered until 1933, and its performance could not match Grumman's. The prototype XFF-1 flew for the first time on the 29th of December 1931. In this first iteration, it was powered by a Wright R1820-E Cyclone, which gave 575 horsepower, driving a two-blade variable propeller. During the initial Navy trials, the XFF-1 met all of the performance requirements, and its top speed of 195 miles at sea level exceeded both the contractual guarantee and the 188 miles an hour top speed of the Boeing F-4B-4. However, the Boeing could significantly outclimb the XFF-1, and this, along with additional naval testing on stability, revealed the need for some modifications. These modifications included a minor redesign of the canopy, the fitting of horn balances to the ailerons, the relocation of the arrestor hook further aft, and a strengthening of the undercarriage mechanism to prevent accidental retraction during heavy landings or while taxiing on rough ground, something that had happened once to some general embarrassment. With these modifications, and following a re-engining to a 750 horsepower version of the Cyclone, the XFF-1 now matched the climb performance of the Boeing, along with having a new top speed of 201 miles an hour, and the Navy placed an initial production order for 27 FF-1s not long after this. The first FF-1 was delivered to NAS Anacostia in April 1933, and was initially retained there for service testing. The next 25 went on to the carrier USS Lexington at the very end of the year, where they replaced the Boeings of VF-5B, one of the carrier's two fighter squadrons. The final aircraft went to VF-1B to be flown alongside Curtiss models operated by this squadron from both North Ireland and aboard the USS Saratoga. Not long after this, the US Navy also took delivery of a second variant of the aircraft, known as the SF-1. This was an evolution of the second prototype, the XSF-1, that had been ordered back in June of 1931. Known as a so-called Scout prototype, it differed from the XFF-1 in a number of ways. The two forward guns were removed to increase the fuel capacity from 120 to 165 US gallons, with the offensive armament now consisting of a 30 caliber machine gun mounted in the upper right wing, the provision for two 100-pound bombs to be carried beneath the lower wings, the replacement of the exhaust pipes and town end ring cowling with a NACA cowling and exhaust collector ring, and the replacement of the engine with a 750 horsepower R1820-84. In 1934, some SF-1s were used to test different payload configurations to see if heavier ordnance could be carried by carrier-borne fighters. This included an experiment in which a 1,000-pound bomb was carried on a sway brace below and behind the port wing. The bomb was so large that a skid had to be installed on the brace, lest it strike the ground. Thankfully, this rather hazardous exercise was only carried out a few times before saner minds intervened, on the grounds that carrying a 1,000-pound bomb with a ground clearance measured in inches, not feet, was probably a bad idea. The FF-1s, which by now had been given the nickname of Fifi, and the SF-1s were generally well liked by their pilots and service crews. They were praised for their high speed, exceptional maneuverability, good handling characteristics, and sturdiness. There were some criticisms as well, though. Due to the placement of the upper wing, their forward vision was somewhat restricted, and the narrow track of the landing gear made them difficult to land smoothly. Many pilots also struggled to get used to flying with the canopy closed, though this was a problem common to almost all early enclosed cockpits due to the greenhouse-style arrangements of struts that made up most canopies at the time. The service life of the FF-1 and SF-1 was quite short. They appeared in that time period of rapid transition that not only saw biplanes give way to monoplanes, but also saw rapid advances in technology across every field in aviation and aircraft design. Furthermore, unlike the British Fleet Air Arm, the US Navy had lost interest in two-seat carrier fighters and scout fighters, and by 1935, after less than 3 years of service, the aircraft were taken from frontline duties. After this, 22 FF-1s were fitted with dual controls and redesignated as the FF-2 Trainer. These were distributed to various Naval Reserve air bases or assigned to Marine Reserve squadrons before ending their days as ground instructional airframes when they were too worn out to be airworthy. Though it was outclassed in a short span of time, Grumman's first fighter found some use with foreign nations in one form or another. After completing their delivery orders for the Navy, they had a fair amount of components left over, and so the GG-1, an unarmed demonstrator, was built in 1934. When the Canadian Car and Foundry Company agreed to build the FF-1 under license in 1936, Grumman sold them the GG-1 to use as a demonstrator for the Canadian Grumman fighter. This license-built model was known as the G-23. Some of these were kept in Canada, with the hopes of selling them to the RCAF, but Car and Foundry also found overseas customers. Their biggest export order was for 50 planes, and this was supposedly placed by Turkey, but it was eventually revealed that it was agents of the Spanish Republican government who had placed the order with forged Turkish papers. This export was then declared illegal by the Canadian government, but some 34 units had already reached Spain before the embargo kicked in, and it was here that the Grumman would see its first and only taste of combat. Known as the Delphin in Spain, it was primarily intended for use in the ground attack role, and it made its combat debut in July of 1938. One of these Delphins gained the distinction of claiming the only victory credited to Grumman biplanes, when its crew shot down a Heinkel HE-59B flown by the Condor Legion. But overall, however, the Delphins did not perform well. 3 were shot down, 6 were captured, and 20 were lost in combat and operational accidents. The Canadians would also use the aircraft, albeit reluctantly, when they realised they could not rely on Britain to supply them with fighters in 1940, Britain being otherwise occupied with the Luftwaffe, funnily enough. 27 G-23s were eventually pressed into service and given the designation of Goblin. Though they apparently saw no combat service, they were for a time the only fighters available to defend the east coast of Canada in a time of Spitfires and Messerschmitts, which was hardly reassuring. Thankfully, this now totally obsolete fighter was never needed to defend Canadian airspace. Aside from Canada and Spain, single examples of the Grumman FF would appear in Mexico, Nicaragua, and Japan. The model that went to Nicaragua saw little service before being consigned to the scrap heap in 1944. There it lay until it was rescued, brought up to flying condition, and flown back to the United States. Restored, it is now, I believe, the only surviving Grumman FF to be found today, and it's on display at the National Naval Air Museum in Pensacola. Though their time was brief, being superseded by more modern designs, Grumman's first fighters proved to the Navy that this new company could be a competent manufacturer of naval aircraft. This they were, and they would soon demonstrate this with such aircraft as the F-4F Wildcat and the F-6F Hellcat. But those are stories for another day.
Episode 14. The Vought Sikorsky OS-2U.
This observation aircraft was a common sight on the deck of a US battleship or cruiser during the Pacific War, and it was a thoroughly welcome sight for the many downed airmen it rescued from the perils of the waves. Though it was an invaluable asset to any ship's company, and a guardian angel to many, its often utilitarian tasks never gave it the same level of fame as other icons of the Pacific. Usually the F-4U Corsair or the PBY Catalina come to mind when you think of that particular theatre, and I hope today's video sheds some more light on this often underappreciated plane. The time of the Kingfisher could be considered the heyday of the naval scout. Before the advent of radar, the scout and observation aircraft served as the eyes of the fleet. They would patrol hundreds of miles of sea, either from a shore base or launched from a ship. They were used to scout the movements of surface ships or submarines, act as gunnery spotters for battleships and cruisers, or act as air-sea rescue units. In the mid-1930s, the US Navy realized that their current observation aircraft, the Vought O3U Corsair, was beginning to show its age, much of its design being taken from the O2U, which entered service back in 1926. The situation was also compounded by the rapid advancements being made in aviation, many of which were rendering certain aircraft obsolete within just a few years of service. In 1937, the US Navy asked all interested manufacturers to submit bids for a new observation scout aircraft. The key requirements of the specification stated that the new aircraft must be a two-seater, it must be small enough to operate from a battleship without the need for folding wings, and it must be able to be easily converted into a land plane to operate from shore bases. 3 companies submitted aircraft to meet the specification. Stearman Aircraft submitted to the XO SS-1, a 2-seat biplane of mixed construction.
The Naval Aircraft Factory submitted the XOSN-1, also a biplane of mixed construction. And Vought submitted a mid-wing monoplane that would become the XOS-2U-1. The OS-2U was designed by Vought engineer Rex Beisel, who by now had over 15 years' experience in building naval fighters, and it showed. Unlike the competition, and to an extent a large number of senior naval officers, he'd cast his gaze abroad, seen what was being built elsewhere, and realised that in a couple of years a biplane would be utterly useless. Not only that, but Beisel wanted a design that significantly outperformed both the existing naval scouts and the competition, and that made going with a monoplane design all the more necessary. Like the submissions by Stearman and NAF, the design that was to become the first OS-2U was also of mixed construction, but to less of a degree. The fuselage was all metal, built around an aluminium monocoque. The mid-mounted cantilever wing was also built up from metal, but only the forward section was covered in a metal skin, with the rear section being fabric covered to save weight. The OS-2U prototype was unique for a number of things, aside from being the first monoplane naval scout. It was the first aircraft design to use spot welding in order to create a non-buckling fuselage structure. This was done by Beisel to tackle the problem of keeping the aircraft light, while also keeping it sturdy enough to withstand the constant stress of catapult launches. It also brought other benefits. Not only was conventional maintenance time on the aircraft to be lowered because of this, but the new construction technique would also help to improve the service life of the airframe. The prototype was also the first to feature drooping ailerons that could be used to act as full-span flaps. To achieve and handle the slow takeoff and landing speeds of seaborne operations, these flaps were necessary, and it was also necessary for the aircraft to have a very low wing loading, which is why it had a relatively large wing surface area of 262 square feet. The ailerons were of course not useful as ailerons when dropped, and so lateral control was accomplished by means of an upper wing spoiler. Per the specification, the aircraft had a crew of 2, a pilot up front in a fully enclosed cockpit, and a crew member in the rear cockpit that would act as a gunner, observer, and radio operator. Both canopies had sliding doors, with the rear canopy opening considerably further so that a machine gun on a flexible mount could be used for defense. Vought submitted Beisel's design in March of 1937. In manner of point, the company was enjoying a bit of a head start, as they had been previously approached by the Navy in 1936 for a new naval scout design, but their previous attempt, a biplane, had not been a big enough jump in performance to order into production, which was yet another reason for Beisel going for the monoplane route. This time, he was confident that his design would be well received by the Navy's Bureau of Aeronautics, but initially this confidence received a bit of a check. Despite some monoplanes entering service, the Bureau of Aeronautics doubted the monoplane's ability to manage the low takeoff speeds of catapult-launched scout planes. When the proposal for the Vought prototype was submitted to the Navy, the Bureau nearly turned it down, as they did not believe the design could possibly meet the weight and performance requirements. In fact, Vought was requested to spend 2 weeks checking and rechecking the weight and landing speeds to make sure some sort of mistake had not been made. Once these checks were complete, the design was resubmitted, no doubt with some heated insistence on Beisel's part that his numbers were in fact correct, and eventually a contract was placed for the construction of the XOS-2U. When complete, it was powered by a 9-cylinder, 450 horsepower Pratt & Whitney R985-4 Wasp. First completed as a land plane, it made its maiden flight on the 1st of March 1938, a full 3 months ahead of the competing prototypes built by NAF and Stearman. The aircraft was later converted to a float plane, with its first flight in this form happening on the 19th of May 1938. Test flights of the float plane model showed a top speed of 171 miles an hour at 5,000 feet, and a landing speed of just 55 miles an hour, the latter being courtesy of the drooping ailerons. Following its initial manufacturer trials, the prototype was sent for naval evaluation at NAS Anacostia in August of 1938, and following these, it was sent to the USS West Virginia for catapult trials. These trials were wholly successful, silencing any lingering skepticism of the monoplane design, and on the 22nd of May 1939, the Bureau of Aeronautics placed an order with Vought for 54 production aircraft under the designation of OS2U-1. As a side point here, during 1939, the Chance Vought Aircraft Division and that of Sikorsky merged their aircraft manufacturing facilities, and Vought Sikorsky came into being. This is why the OS2U is sometimes referred to as the Vought Sikorsky OS2U, but in reality it was pretty much all done by Vought, as Sikorsky was busy working on helicopters and other rotary craft. The first order of 54 OS2U-1s were delivered between May and December of 1940, and these first production models differed from the prototype in several ways. It was now powered by the R985-48 variant of the Wasp, which used a longer exhaust stack. The leading edge of the observer's canopy was squared off. It now had a radio direction finder installed in the rear cockpit, and the float was changed from the Vought design to ones made by EDO. This float, unlike the more pointy Vought model, had a rounded bow and a different rudder shape. It also had a stouter rear support strut to cope with rough seas. The armament layout was also finalized. The OS2U-1 was armed with two 30-caliber machine guns, one in a fixed forward-firing position operated by the pilot using the Mark III telescopic gun sight, which some loved and some hated, and one in a flexible mount that was used by the rear gunner. As the chance of being dragged into a war became more likely, either due to the deteriorating diplomatic situation with Japan, or due to somebody in Europe doing something catastrophically stupid enough to warrant American involvement, it was decided to improve the offensive capabilities of scout planes. The OS2U-1 was thus fitted with underwing racks, one per wing, that could accommodate either a 100-pound bomb or a 325-pound depth charge. Though it was now different from the prototype in several ways, overall the physical changes were minor, and so the performance figures of the production model were generally the same as the prototype. Upon completion, the first production aircraft were delivered to Observation Squadron 4, VSO-4, aboard the battleship USS Colorado, making them the first monoplanes to serve aboard a US battleship. Of the original order of 54, 49 were built on floats and assigned to various battleships and cruisers, and the 5 land planes were assigned to shore bases. Later on, the first OS2U-1 to roll off the production line was later loaned to Northrop in 1941 to test out a set of so-called Zap flap wings. These were designed by Ed Zapp. They were a new style of full-span flap wing that were intended for use on the upcoming P-61. The new wings increased the OS2U's wingspan to 36 feet and 6 inches, and the Zap flaps were manually controlled from the cockpit. In the end, the P-61 never used the wing due to production tolerances, but 2 more OS2Us were fitted for experimentation and later designated as the X-OS2U-4. Before the first production batch of 54 OS2U-1 units had been completed, things were already moving on. On the 4th of December 1939, the Navy issued a production contract for 158 improved variants designated as the OS2U-2. Externally, the OS2U-2 was identical to its predecessor. Internally, however, there were a few changes. It now had self-sealing fuel tanks, additional armor protection, and additional fuel tanks mounted in the inboard wing panels. This increased the fuel capacity by 96 US gallons, giving a new total fuel capacity of 240 US gallons, or approximately 908 litres for those of us who use metric. The fuel system was also protected by a CO2 gas purge system to prevent the buildup of explosive vapor, which was nice. All of these changes added weight. and this did reduce the top speed by 7 miles an hour. But this was considered an acceptable trade-off, and no further modifications were made. Unlike the first batch, the majority of OS2U2s were completed as land planes, with only 45 out of the 158 delivered built as floatplane models. Many of these aircraft, at least 99 according to company records, were used to form inshore patrol squadrons that were either land or water-based, depending on operational need, and they would be operated from coastal bases in the continental United States, Alaska, Panama, as well as bases scattered across the Pacific. In what was now becoming a theme of rapid iteration, the OS2U3 came into being in May of 1941, not long after the previous variant had first entered operational service. It was also during this year, specifically in October, that the OS2U was given the name Kingfisher by order of the Secretary of the Navy, and this name was applied retroactively to all existing units. The third variant of the Kingfisher was the most widely produced, with 1006 being built by Vought, and a further 300 being built by the Naval Aircraft Factory as the OS2N. Externally, they were identical to the previous variant, but again, like its predecessor, there were internal changes. It was now powered by a 450 horsepower Pratt & Whitney R985AN2. The AN designation indicated that this engine was common to both the Army and Navy, and that parts could be used interchangeably. This was a welcome change, as previously many engines had a different designation for each service, even though the engine itself would be identical, and this led to confusion when it came to parts ordering, especially if the aircraft from one service found itself being looked after by the other, for whatever reason. Having a universal designation sped up the ordering process and made general parts and maintenance a lot easier. In a first for the series, it was equipped with a bracket on the starboard side to mount a Fairchild gun camera. The camera itself was bulky and cumbersome, and it was installed only for training and gunnery practice, rather than for recording actual combat. These changes, made to the OS2U2 and the OS2U3, had brought the range down to 908 miles, which was almost a 10% reduction on the original. But this was deemed acceptable for a few reasons. 1. The extra protection offered to the crew was welcome, as even a small amount of extra armor can do a lot for survivability. 2. The extra fire prevention system was welcome, for obvious reasons. And 3. The further a scout travelled from its mothership, the more difficult it was to navigate back, and therefore the more easier it was to get lost. So, even though the effective range had dropped, a 905-mile range still gave an extreme operational range of 450 miles if the pilot liked running on fumes, which was still a huge amount of sea to cover, and so the loss of 80-ish miles wasn't a huge problem. Once it was operational in numbers, the service life of the Kingfisher was remarkably varied, and it found itself serving aboard a number of different naval vessels. By the time of the attack on Pearl Harbor, 17 of the 18 commissioned battleships were now fully equipped with Kingfishers. The USS Wyoming was a gunnery training ship and didn't need them, and Kingfishers were also used aboard the Omaha-class light cruisers. Before Pearl Harbor, the units aboard battleships were made up from units of VO1 through to VO5 observation squadrons, whilst those aboard cruisers consisted of units from VCS-3 through to VCS-9 cruiser scouting squadrons. After Pearl Harbor, this changed. The organizational side of the VO and VCS squadrons basically became a thing of the past, and the aircraft and men became a part of a ship's company, with replacements being assigned to the ships on an as-needed basis. Though this simplified the management of the aircraft from an administrative perspective, they now being the ship's problem, it presented headaches for the crewmen and officers who used them. Almost all maintenance work for the Kingfishers could be carried out at sea, barring the most extreme cases, but parts and equipment were still finite.
In a perfect world, any parts or equipment could eventually be sourced when the ship put into a port where there happened to be a naval air station. However, it was quickly discovered that said stations had not been given an organization plan that now reflected the independent and flexible nature of the Kingfishers being the ship's problem rather than the squadron's. When the spare parts were needed, no one seemed to know where they were, or if they did, they often didn't have the logistical authority to release them to the Kingfisher crew. More often than not, these Kingfisher units attached to battleships and cruisers found that they were completely on their own in terms of being responsible for parts and maintenance at port, and in consequence, their pilots and crews had to resort to the age-old, well-known naval system of midnight stores. It was quickly understood that when spare parts were needed for your Kingfisher, you liberated them under the cover of darkness. When their crews weren't ashore, plundering warehouses by night, Kingfishers attached to battleships and cruisers provided much-needed support during the early stages of the US Navy's involvement in the war. With a distinct lack of escort carriers, protection still had to be given to the Atlantic and Pacific convoys. Battleships and cruisers assigned to convoy duty provided the tactically and psychologically important air umbrella. A constant patrol was kept through the daylight hours, and each OS-2U was usually equipped with depth charges or bombs. In the event that an enemy submarine was spotted, the Kingfisher would engage it, harassing the submarine until the escorting destroyers could close the range and turn the harassment into a depth charge-filled nightmare. Speaking of destroyers, OS-2Us were used in an experimental program that saw 6 Fletcher-class destroyers modified to carry scout planes. The rotating catapult was placed where the No. 3 main battery and aft torpedo tubes were normally placed, and a tank with 1,780 US gallons of aviation fuel was installed on the main deck, and this was surrounded by a cofferdam filled with CO2 for obvious safety reasons. Problems with the hoisting equipment led to the removal of the aircraft from 4 of the destroyers, but the USS Halford and the USS Stevens enjoyed good success with their Kingfishers. Overall, though, the project was canned. Recovering the aircraft was too much of a headache, as the destroyer did not produce a large enough area of calm sea in its wake for safe landings when it was underway. The alternative was for the destroyer to come to an almost complete stop to pick up the aircraft, which in wartime is not ideal. During heavy seas it was even worse, and the aircraft were often damaged when striking the funnel, and the giant tank of aviation fuel on the main deck was equally disconcerting. Eventually, in December of 1943, the USS Stevens and Halford had their aircraft equipment removed, and the brief era of float planes on destroyers came to an end, and it was probably for the best. Kingfishers would take part in all the major actions of the Pacific War, from Guadalcanal to the Marshalls, the Gilberts, the Marianas, the Philippines, and onto Iwo Jima and Okinawa. They stalked the Japanese fleets, harassed submarines, and provided observation for ground troops, as well as gunnery spotting for their own ships. But the role they are most remembered for is that of the guardian angel that rescued many a downed pilot who was stranded at sea. In this role, 2 particular events stand out. The first of these happened in 1942, and to be fair, it stands out more because of the person that was rescued rather than the plane itself, but it's still worth talking about. In late October, a US Army Air Force B-17 had been forced to ditch in the Pacific due to a navigation error. For nearly 3 weeks, an unrelenting search was carried out for the 8 missing airmen, particularly as among them was Captain Eddie V. Rickenbacker, Medal of Honor recipient and the highest-scoring US fighter ace from the First World War. His salvation, and indeed that of the whole crew, bar one who died of dehydration, came in the form of an OS-2U. This particular OS-2U had already lived a busy life. It had survived the attack on Pearl Harbor, and at some point during its service life it had received the nickname of the Bug. Over 2 days of searching, it found the missing men, and on the second day of rescue it found Rickenbacker and 2 others. Unable to fly all 3 survivors back in one go, the decision was made to taxi across 40 miles of ocean to the nearest island, with Rickenbacker and 1 other crewman lashed onto the wings. The second rescue event of note happened in April of 1944. Personally, I think this event stands out more as it is a better testament to the Kingfisher's durability and its ability to handle rough water. It occurred when the US fleet was beginning its assault on the Japanese stronghold of Truk Atoll. Though there was little Japanese air presence during the battle, heavy anti-air fire kept the Kingfishers of the battleship USS North Carolina very busy. Events began on April 30th, when the 2 Kingfishers, the first flown by Lieutenant J.J. Dowdall, and the second by Lieutenant J.A. Burns, were circling over a downed pilot, Lieutenant Keynes, from the USS Enterprise. Dowdall took his Kingfisher down for the pickup. However, the water was rough. Lieutenant Keynes was forced to cling to one of the wing floats as his raft was swept away, but the added weight then caused the Kingfisher to capsize when it was caught by a wave. Witnessing the unhappy turn of events from above, Lieutenant Burns brought his plane down and carefully taxied over to the downed pilot, and the now equally waterlogged Lieutenant Dowdall and his rear gunner R.E. Hill. Burns and his gunner, A.J. Gill, helped the men aboard. To balance the float plane, Keynes was placed on one wing, Dowdall on the other, and Hill was hung on the fuselage. Burns then taxied the 5 of them across the water, in an active war zone, to the rescue submarine USS Tang, where he deposited his now even more soaked passengers. The USS Tang then went over to destroy Dowdall's ditched Kingfisher, to keep it from falling into enemy hands. Immediately after this, Lieutenant Burns was directed east to where another pilot had been reportedly downed, and the USS Tang was directed to cover rescue operations. Burns found the downed pilot, Lieutenant R.T. Barber, but again, the added weight made it too difficult to take off in the rough seas. And so, Burns radioed the USS Tang to come over, and while they waited, Burns, Gill, and Barber sat bobbing on the waves, watching the other carrier aircraft continue to pummel the fortifications at Truk. As they watched the assault, which must have been surreal to see from such a position, 2 Grumman TBF Avengers, flown by Lieutenant R.S. Nelson and Ensign C.L. Farrell, received damage from anti-aircraft fire and also had to ditch. As the USS Tang was known to be on its way, Burns declared his intention to try and rescue them as well and get everyone to the submarine. He taxied over, which took about 30 minutes in the rough conditions, reaching Lieutenant Nelson's raft first, which contained said pilot and his 2 crew members. Burns tossed them a line and proceeded to tow the life raft over to the second, which contained Lieutenant Farrell and his 2 crew members. Burns then attempted to tow both life rafts to safety. This proved impractical, as the increased drag forced him to increase the engine power, and this resulted in a backwash of wind and water so shocking that it threatened to drown the very people that Burns had rescued. After giving them the power wash treatment, Burns transferred them all onto the Kingfisher, placing some on the wings and others on the fuselage to try and balance the load, and he resumed taxiing towards the USS Tang. The Tang then received another emergency call, disappearing beneath the waves to go off and save yet another downed pilot, probably as the thought of Burns adding any more weight onto his already overloaded Kingfisher was by now comical. When it returned, the waves had finally taken their toll. Burns's Kingfisher had started to take on water in the main float, and it was starting to list. All 9 aviators were taken aboard the Tang, and for its services of rescuing 10 men in the space of a single day, Burns's Kingfisher was then sunk by the guns of the USS Tang, again, to keep it from falling into the hands of the enemy. The ruggedness of the OS-2U, as demonstrated in the hands of Lieutenant Burns, endeared it to its crews and the fortunate souls that it often flew down to rescue, but it also performed its other roles to admiration, though they were often thankless tasks that never covered them in the same glory. Doing said tasks, it enjoyed a remarkably long service life in the US Navy, serving well into the late 1940s as a training and patrol aircraft. Admittedly, this long service life had not been planned, but rather it was forced upon the Kingfisher by the complete failure of the Curtiss Seamew, which we recently covered on this channel. The Curtiss SC Seahawk started to replace the Kingfisher in October of 1944, but it was a slow process. Along with dutifully serving the US Navy, the Kingfisher would also find service overseas. The final variant, the OS-2U3, was the only model to be exported. Chile received 15 aircraft under a Lend-Lease agreement, 6 went to Uruguay, 9 to Argentina, 6 to Mexico, and 3 to the Dominican Republic. The Dominican Kingfishers were reportedly later transferred to Cuba, and these were apparently used to bomb government troops during the final stages of the revolution, the largest evidence of this being the sole aircraft on display at the Museum of the Revolution in Havana. The two largest foreign operators of the Kingfisher were Britain and Australia. The Royal Australian Air Force received 18 aircraft that had been relinquished from an original order of 24 that were en route to the Dutch East Indies when the islands fell. These were used by the newly formed No. 107 Squadron, and they were flown primarily on anti-submarine and convoy escort patrols. They were also used in experiments for a new camouflage scheme. When delivered, they were painted in the overall light grey and forest colours of the Dutch Air Force, which were highly unsuitable for Australia, even our rainforests here are dusty, and new colours were soon adopted. Sadly, there doesn't seem to be any photo record of this, but numerous sources say that this happened. The Fleet Air Arm of the Royal Navy would receive 100 of the Kingfishers, and instead of renaming them like they sometimes did with imported models, they kept the name. The Kingfisher was slated to re-equip certain cruisers and armed merchant cruisers that could not launch the Supermarine Walrus, the then standard catapult aircraft of the Royal Navy. Operating in all types of weather, the Kingfishers operated by the Royal Navy would serve just as well as their US counterparts. During July, August, and September of 1943, Kingfishers and other float planes from the armed merchant cruiser Canton and the light cruiser Emerald made up the only air strength of the Eastern Fleet in the Indian Ocean, as the Royal Navy could not spare an aircraft carrier for this time. By the end of April 1944, catapult aircraft had been phased out of the Royal Navy, and most of the Kingfishers were then decommissioned from Fleet Air Arm service. Due to their high production numbers and extensive use, several models of the OS-2U3 survive today. Unsurprisingly, most are on display in the United States, but others can be found in Australia, New Zealand, Chile, and Cuba. The OS-2U Kingfishers served longer than expected, and did more than expected. Though it was often thankless and unglamorous, their service would span the entirety of the United States' participation of the Second World War. They even managed to melt many a reserved heart in the Fleet Air Arm, though many of them would still claim the Supermarine Walrus to be their particular favourite float plane. But the story of the Walrus is one for another day.